Am I audible?
Yes, sir. You're audible.
Sir, we post okay. We can admit it, but let us first set up the camera.
Sir, in the meantime, just add that banner, maybe, or you want me to add a banner?
NES. It screen share for the banner screen share. Specializing in prepaid LPG. The window समस्त वाला होता है separate access होता है.
I shared one banner.
आपने कर लिया?
For the time being.
Okay, ठीक.
सर को सर को हम
Yeah, I'm trying to see. I think you can just.
First one.
सर मैं एडमिट कर देता हूँ लोगों को.
जी सर.
Okay, everyone is coming. Admit all.
So let us disable the waiting room too.
Yeah. Okay, great. Good morning, everyone.
Good morning, sir.
Good morning. Okay, great. I think everyone is here. So we will start the things in another couple of minutes. Sir, we can't hear voice.
Advanced VLSI Lab was set up in 2012, an initiative by Department of ECE and AEI in collaboration with Sankalp Semiconductor. Primary objective: to bring our VLSI academic framework closer to the industry and prepare engineering graduates for the challenges in the industry. Conducted industry-grade trainings in the VLSI domain. First major research and development activity resulting in a fabricated chip in a 180 nanometer CMOS in collaboration with Sankalp Semiconductor Private Limited and NIST Berhampur, Odisha. Funded by India Chip Program 2016. State-of-the-art information and technology and computing infrastructure with enterprise-grade electronic design automation, that is EDA tools from Cadence and Mentor Graphics, along with open source EDA tools. NDA in place with major semiconductor fabrication founders in the world, giving access to state-of-the-art IC technologies for fabrication. Industry collaboration with major semiconductor companies and skill development institutes to bring world-class research and development experience and industry-grade skill development programs to the engineering students at Silicon. An indigenous, fully in-house chip was designed by 12 undergraduate students in 600 nanometer CMOS technology, fabricated by ExpertTalk, Germany, and fully tested for functionality and performance. In 2019, an extension to the advanced VLSI was added to provide a modern office space environment for industry training and research development work. The lab is equipped with fully networked workstations and AV equipment for fully functional local and remote office environment. In December of 2019, we furthered our goal of bridging the gap by bringing the industry closer to academia. Conducted NES2019, a 4-day workshop, nanotechnology and embedded systems. Eminent speakers from the top semiconductor companies and industries including Synopsys, STM Microelectronics, Savia, VSD, VLSI experts, Tufts University, IIT Kanpur, IIT Kharagpur, IIT Roorkee, KVEC, Makot, and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students, and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micron through our close partner Savia Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by ExpertTalk, Germany. In 2019, another extension to the advanced VLSI was added, a fully operational industry-grade characterization lab capable of industrial-grade temperature characterization up to 1 part per million accuracy, a capability only few colleges in the world are capable of. Use of industry-standard test and automation tools such as LabVIEW, LabC Windows, and Python. Advanced VLSI Lab was set up in 2012, an initiative by Department of ECE and AEI in collaboration with Sankalp Semiconductor. Primary objective: to bring our VLSI academic framework closer to the industry and prepare engineering graduates for the challenges in the industry. Conducted industry-grade trainings in the VLSI domain. First major research and development activity resulting in a fabricated chip in a 180 nanometer CMOS in collaboration with Sankalp Semiconductor Private Limited and NIST Berhampur, Odisha. Funded by India Chip Program 2016. State-of-the-art information and technology and computing infrastructure with enterprise-grade electronic design automation, that is EDA tools from Cadence and Mentor Graphics, along with open source EDA tools. NDA in place with major semiconductor fabrication founders in the world, giving access to state-of-the-art IC technologies for fabrication. industry collaboration with major semiconductor companies and skill development institutes to bring world-class research and development experience and industry-grade skill development programs to the engineering students at Silicon. An indigenous, fully in-house chip was designed by 12 undergraduate students in 600 nanometer CMOS technology, fabricated by ExpertTalk, Germany, and fully tested for functionality and performance. In 2019, an extension to the advanced VLSI was added to provide a modern office space environment for industry training and research development work. The lab is equipped with fully networked workstations and AV equipment for fully functional local and remote office environment. In December of 2019, we furthered our goal of bridging the gap by bringing the industry closer to academia. Conducted NES2019, a 4-day workshop, nanotechnology and embedded systems. Eminent speakers from the top semiconductor companies and industries including Synopsys, STM Microelectronics, Savia, VSD, VLSI experts, Tufts University, IIT Kanpur, IIT Kharagpur, IIT Roorkee, KVEC, Makot, and MSEC. The 4-day event electrified the audience with 11 expert talks on wide-ranging topics, 3 workshops, 3 open house discussions with students, and a very insightful panel discussion. In March of 2020, we were proud to have placed 2 of our BTech graduates in Synopsys, a world-leading semiconductor company, for a full-time position. We are also proud to have our graduates working in other leading semiconductor companies such as ST Microelectronics and Micron through our close partner Savia Multimedia. In September 2020, we collaborated with Boston Microtechnology to develop analog intellectual property blocks for a high voltage power management integrated circuit. The chip is fabricated using a 180 nanometer CMOS technology by ExpertTalk, Germany. In 2019, another extension to the advanced VLSI was added, a fully operational industry-grade characterization lab capable of industrial-grade temperature characterization up to 1 part per million accuracy, a capability only few colleges in the world are capable of. Use of industry-standard test and automation tools such as LabVIEW, LabC Windows, and Python.
Hello, everyone. Hi, Rohit.
Hi.
Yeah, so I think we will start in a couple of minutes. Yeah.
Is
Good.
that Puneet talking to?
Yes, it's Puneet. Somehow you can't see me, but I can see you. So you're the same as you looks on in your photo. Usually people share like 20 year before photos, so that's the reason.
So that's a good news or a bad?
It's a good news.
Okay.
So you are still looks very very young.
Okay. Well, I take that as a compliment.
Yeah.
Hi Rohit, this is Saroj here. Good to have you.
Hi, Saroj. Nice to see you.
Yeah, nice to see you too. And thanks a lot for joining. We'll start in like maybe 5 minutes. We're just waiting maybe for a couple of more. Right, Puneet? So is it okay? Maybe wait another 5 minutes?
Yes, I think we can chit chat with Rohit in the meantime.
Yeah, sure. Yeah, this might be the only time we got. He's a busy man. so how is weather in California now?
Oh, weather in California is good. Today it was like a little weird. Sun can't seem to make up its mind. I remember at 12 p.m. talking to my son, and I was confused whether I should put a jacket on or not because it would be too hot in the room because we open our windows during the winters, and so I was
You're in
not
Bay Area, right? You're in Bay Area or Southern California?
in the Bay Area.
Bay Area, right. Yeah, it gets chilly, right? In winters, it gets chilly. I remember sometimes being in December and it gets really chilly.
It's actually relatively hot this year. I mean, the temperature is still 45, 65.
Okay.
Yeah, but it's not used
Okay,
so
okay.
out. It doesn't matter. The COVID is everywhere.
Right. And you had those huge fires too, right?
Yeah. Yeah, that was another 2020 movement. So the fire back in August was like, and I used to say this during that time that fire is spreading like COVID and COVID is spreading like fire. And fire wants you to stay
Yeah, that's
indoors.
funny.
And so COVID wants you to stay indoors and fire wants you to get out. And this is 2020 conflicting events right there. Yeah, so fun times,
Yeah, it's been a weird year, but
Yeah, no, it'll be remembered long time, right? So just like 2001 in US is a huge, has this 2020. I don't think we realize the kind of history we are making right now. 40 years from now, our kids will remember 2020 like
right.
World War II or something. This is something big, and changes are happening
Yeah,
quietly.
exactly. I mean, it's if you take correct.
But I can't
We have a
complain.
little bit of
Being
a
the
lag
guy
in our.
behind the screen most of the time, it's just funnier.
So there is a lag between Rohit, between you, me, means we both have sync 100%, but there is a lag between us and the Saroj sir. So several times you will see like, okay, when he was talking, we are also
Oh,
talking.
I see. So it's from this side.
Yeah, it looks to be maybe. I don't know. At least I think me and the Rohit, we are synced properly. But
Okay, just give me a second. I'll just change my. I think. Should have this way.
so Rohit, and everyone, like we are also live on YouTube right now. And I just shared the YouTube link if you want to share with any of your friend or those who can't make it right now or just because of the bandwidth.
No, thank
So
you. So you will keep it public, right?
Yes, I think it's a public. It will be public air.
Okay. Yeah, I can use that later. Thank you
Yeah.
for
So the
letting me know.
the reason I thought like okay I should just share with you so that you should know like okay it's a live so and it's going to be over the net. So yeah, so that's the thing. I think we are good crowd early in the morning now. So right yesterday it was the attendees was too good and I think you already know like okay yesterday we have a couple of sessions by one session is by Shivanand Koteshwar from Synopsys, one is from Vishal from Micron, and in the evening so like, Indian time evening it is like there was a one workshop with Steve over.
So you guys do that every year? Is there a rotation?
So it's like SIT is doing every year. So last year also they did it NES 2019 and the same time frame almost maybe even not the same time frame maybe I think it's 25th 26th sir it's near about that those dates if I'm not wrong.
Sorry, can you repeat? We were switching. I think we fixed the delay
Okay.
problem now.
No, so Rohit was asking like, okay, is it a annual event or it's a so monthly
Yeah,
event? So I
yeah.
was saying, yeah.
Right. So we started last year. Actually, last year is the first time we started the NES 2019. We almost thought of skipping it this year because couldn't hold it, and then we kind of made a last-minute decision, and I'm glad we did because this turned out to be a great event so far. So a lot of participants and. So,
Dr. Saroj, do you know Dr. Srinivas Bopu in IIT Bhubaneswar?
no, actually, I don't have any contact with IIT Bhubaneswar here. They don't have a big VLSI activity here. Yeah, I'm not. I honestly I haven't even visited them yet. We just haven't had any contact with them. They used to be very close by to our college. Now they're on the outskirts of Bhubaneswar. So yeah, I haven't met him. Sorry. So is he a friend or colleague, or ex-colleague of yours or someone? Or?
No, we have similar interests. We've been talking for a few years now about number of different things, and I thought, maybe he instigated this conversation, or I was just wondering whether is there a connection.
I see. Now this was purely from Puneet's side. Actually, your contact is purely from Puneet's side. So yeah, I didn't know the professor from IIT Bhubaneswar. Okay, Puneet, should we start? Maybe we can do a Q&A. We can chat.
Yes, sir. So already
Okay.
attendees are also coming. I think this is good time.
Yeah, I think we have a good forum. Let's start.
Okay.
Sorry, Rohit. Sorry, just give a second. The anchor is going to introduce you, and then you can start right away.
Good morning, everyone, once again, and welcome to the second day of the webinar, NES 2020. Now, moving forward to the technical sessions, we have Rohit Sharma here. He is an engineer, author, and entrepreneur. He is currently the founder and CEO of ADS USA. He has founded 2 companies, published several papers in international conference and journals, and authored 2 bestsellers books on machine intelligence and VLSI cell characterization. He has contributed to the ML and EDA domain for over 20 years. He is the lead architect of DeepSeek and open source deep neural network compiler library and framework. So now I would like to request Mr. Rohit Sharma to share his experience with us. He will speak about the principle and application of TinyML.
Thank you for the nice introduction. Guys, greetings of the day. I am Rohit Sharma. And the intent of the meeting or this talk is to inspire some of you guys to think about learning more about TinyML and possibly develop some of the applications. And during the course of this lecture, I hope to convey that how easy it is to create new applications on smaller devices. So before I start, what TinyML actually begs some explanation as to what TinyML is, right? So I hope most of us have heard the term machine learning, which is ML. On machine learning, AI, deep learning, I mean, slightly different concepts, but part of the same wave that started back with deep learning in 2012, when there was a video that Google's Jeff Dean was able to sort of classify the cats on the YouTube video with the LXNet. And so that started making wave in 2012, and now we are in 20, almost after 8 years. The applications of machine learning and specifically deep learning are sort of disrupting most of the verticals and bringing out newer markets and industries. So I would not go into the boring details of what machine learning, the definition and stuff like that. If you have a question, feel free to ask me. I'll try to put it into simpler words that is understood in a spoken language. So putting tiny in front of ML is essentially saying that how can we run these machine learning models into tiny devices, right? So what are tiny devices? So this is one of those that you see in my hand. This is small microcontrollers that can go into one of the edge devices. And it has practically everything to run a small application on the processor that you see here. This is ARM M4 embedded processor, and it has a 256 kilobytes of RAM and has several sensors. So the useful part of most useful part of this is like half the board. So these are very tiny devices and very low power devices that can run on a coin battery for up to a year or more. So if you happen to have an application that is running on these devices, you can make it work on deep space. You can make it work in the deep jungles, forests, where electricity and light and some of the networks are difficult to reach. They will run for several months to a few years, and that opens up a very large spectrum of applications. And that gets me excited every time we think about or I talk about TinyML. So in this lecture, I hope to talk about TinyML tools and applications, and give you some rundown as to what we as a company, AI Technology and Systems, are doing in that domain. How easy is it? We are trying to sort of make that if you have an idea of helping or creating something new, we make it easy. So long as you know Python or are willing to learn Python, that is the only requirement. Then you can create some of the boards like the one you saw in my hand. So with that, let's get started. The agenda I'm going to follow is we will talk about applications and use cases, and I'm going to talk about sensor ASL and backward detection. So sensor ASL is essentially an application which works on a couple of sensors, and those sensors are gyroscope and accelerometer. So gyroscope is a sensor which sort of gives you the location. An accelerometer tells you how fast the object is moving, that embeds the accelerometer. So with these two sensors, you can create an application which can decode the sign language. So ASL stands for American Sign Language, and every country has their version of sign language. So I'm going to talk about ASL, but the same ideas are applicable to other sign languages too. And if you talk about mute people who speak sign language, for example, I never picked up sign language, right? Mostly because I don't need it, but that doesn't mean that the number of mute people in the world are any lower. So there are 70 million mute people that use the sign language. So to give you an idea what sign language is, this is when you do this sign is hi, and this is how are you. So you know they move their fingers and hands and gestures faster, and that's where this idea is that if you add sensors like gyroscope and accelerometer on the fingertips when they are moving their fingers in a way that can capture the movement and create a data set that we can learn or train a machine learning model that would decode these words. The way they are moving, that would decode what kind of word they are speaking, right? And that in conjunction with your natural language processing can create a beautiful application which can take an ASL sign and convert it into a spoken word and sentences. So now that's the application side, but imagine the beauty of that application, right? If you give it to 70 million people, then it opens up, beautiful conversations with the mute population and the rest of the world, which is another 7.5 billion people. So the connections that they would forge would create a new, new type of relationship, new type of ideas and stuff. Right now, if somebody is mute, they want to talk to me, I find myself disabled, primarily because I don't know my disabilities, I don't understand the sign language, and I feel bad about that. And that would bridge that gap for me. So that's the level of excitement that I see on a daily basis using some of these applications. And so number 2 on the list is wake word detection. And that essentially is when you talk to some of these smart speakers like Hey Siri or Hey Alexa or Hey Google, what do they do internally? And I would tell you that they're using something similar that I will share with you. Essentially a DSP running on a very low power, which when spoken to, the hardware is mostly sleeping, not sending anything to the cloud until you say that wake word, and then it wakes up the whole hardware. It sends the signal, and then Mike wakes up the rest of the hardware, including Wi-Fi and GPRS modules. They wake up, and rest of the speech is recorded and sent to cloud where NLP engines are running, and then the response is sent back to the device, like smart speaker or your cell phone. And that's how you that's how you hold conversation. So I'm going to talk about these 2 applications, and then we will talk about framework, tools, and techniques. Essentially, most of the technology that is used in creating these applications, and I'll talk a little bit about algorithms and optimizations. Like I said, this is a vast area and slightly more technical than most. I would like to leave some motivation in the crowd that this might sound intimidating, but trust me, it is not. We are making it easy on a daily basis. So if you have an idea, would like to work, we have helped over 1,000 people and students and professionals around the world without obligation to create them and help them with their application. And I'll share some of the free resources that you would have at your dispense to go and experiment and create some of these beautiful applications. Okay. And of course, questions. If you have any questions, feel free to stop me at any point. The idea of this whole talk is to, like I keep saying, motivate you guys to learn some of the newer technologies that will enable the future and disrupt many verticals and markets and industries. So stop me, ask questions. I'll be happy to answer as long as they're related to TinyML. So what is TinyML, right? These are some of the keywords that are used. And this Venn diagram is beautifully captures. You might have seen it in other places as well. Artificial intelligence is a very large domain. Machine learning is part of that, and deep learning is another subset of machine learning. And some of the keywords that we'll be using in our slides is network. When I say network, it means cloud and edge. Edge is generally something where the network ends, for example, the cell phone. And then it receives the data, and the data doesn't go anywhere. It sends it back to the servers. So there is nothing else that is connected to your cell phone. Meaning cell phone is the last part of your network. And cloud is essentially a network in itself. It could be a private cloud or public cloud, like a large network. And in context to ML, I'll use model, training, and inference. Model is depending on the context, means many things, but it's capturing the behavior of the data, that is underlying pattern of your data set, and creating some sort of program or algorithm or an equation, depending on the way you look at it, and learning from it and capturing that essence into the model. Training is when you provide the data set, and the model that you created, it could be a neural network, it could be something else, is learning and optimizing the parameters that are present in the model. So that is training. Inference is when the model is done training, model has learned to an acceptable degree of accuracy, then you put that model to work. Essentially, you're training it because it is useful for something, and when you are done training, you refine it and put it for inference. So that part is called inference. The difference between training and inference is kind of technical, meaning you don't do backward propagation in inference. Inference is simply forward propagation. Training requires backward and forward both. And if you need more explanation, talk to me and I should be able to give you more details on that, but not required. On the hardware side, we'll talk about IoT, MCUs or edge devices or tiny devices. Some of these things mean the same thing, meaning you have Internet of Things. If there is an MCU with the Wi-Fi or GPRS module, it becomes an IoT because IoT is Internet of Things. So whatever processor you have with a Wi-Fi module, you can connect it to anything you like, and that becomes an IoT device. MCU is, it may or may not have a Wi-Fi module. So MCU is something that is spread all around us. If you are staying in your house or wherever you are, a typical household has about anywhere from 20 to 50 microcontrollers, and they're hidden. You may not realize that a microcontroller is everywhere. The car you sit in the car, in a standard 20-year-old model, let's say model from 2000, would have about 30 microcontrollers all around you when you sit in a car. There are microcontrollers in your TV, in your refrigerator, washer, dryer, vacuum cleaner, even your toaster, your microwave oven, and even your DSLR, thermostat, you name it. If it is an electronic device, most likely that device has some kind of microcontroller. And there are over 300 billions let me repeat that number, 300 billion microcontrollers in the world today. And we are living all around those, or they are living all around us. It's a old technology, like, before processors, microcontrollers were the thing back in 70s, even before I was born. So, and they have existed for a long time, really mature technology. Now, the difficulty of machine learning running on IoTs or MCUs is they don't have enough power. They are bare metal. What I mean by bare metal is there is no OS running. For example, your laptop has Windows or Linux running on it, and that makes things simple, meaning you can look at your directory, the file structure underlying. You don't have to think about whether I have a hard disk or do I have a mic. In the devices like these, the one you see in my hand, it doesn't have any operating system. And what that means is you will have to design everything on your own for this. And so there are GPIOs, all these, there are 10 general purpose IOs that you can use for that program, and some of the more technical details that embedded engineers or people who have studied embedded systems would know. But the idea of bringing that bare metal into the picture is that these devices are so tiny that they can't even have an operating system. Operating system is too large for them to have. There is something else that's called RTOS, or FreeRTOS, real-time operating system, which is, it's not really an operating system. It's some kind of a task scheduler that people call operating system, or RTOS, that can be brought onto these devices. The benefit of these devices are essentially low power, right? Like I said, they can run for years, and low latency, because if you don't want to send some of the data back to the network, it saves you bandwidth, right? And security. By security, what I mean by that is that if you send something onto another network or another machine, it is always possible that people can intercept that data, hack, and make use of that without your knowledge. So the best kind of security is that you don't send the data anywhere. And if you enable that, that means your device is secure. And so let me give you an example on that. For example, there are passwords, right? We all have, probably over 50 passwords for different sites and services. Now, if that is hacked, you can change your password and go on living your life without thinking about that much. Now, passwords can be replaced by a biometric, for example, iris of your eye, or a fingerprint sensor, for example. And if that is the case, for example, my phone has a fingerprint sensors. When I touch it, it opens up the screen, and that is my sort of password to open the cell phone. Now, let's say if those 125 or 129 points that it is sensing out of my finger, and looking at the distribution of those points to detect whether it is me or somebody else, before it opens the cell phone for me, has a lot of information. Now, let's say it is sending that information over the cloud, over the network, and somebody has enough information to decrypt that information. That means they technically have everything that I have access to. And if that happens, if the information is compromised, that simply means I'll have to lose my finger, because it's not a password that I can change. And I have limited fingers, unfortunately. So that conveys the urgency of that security, as to somehow, sometimes it's not wise to transmit the data because of the security reasons. So what are the steps of TinyML development? TinyML development is similar to ML development with few steps on top, because it doesn't have operating system. So similar to classic machine learning development, you gather the data as a step one, then you design your network or the model. Number two, then you train the model. And then once you're done training, you validate whether the model is good enough. If it's not good enough, then you go and find and debug this stuff. It could be that, let's say if you're using neural network and you started with 100 samples, the sample size is not good enough for that data set. So you would go increase the data set. Or you might want to change your design of the network. You might want to add more neurons, more layers. You might want to add different type of activation function and so on and so forth. But the idea is that you loop if your accuracy or the performance of the model is not good enough. And this is classical, machine learning that all the courses pretty much would teach you. So it's the same machine learning that the first 4 steps is brought here. Now, what is different in machine learning, tiny machine learning is you design your apps or compile the model, and then on that you design the application. And why is that? The reason is that the devices, the bare metal devices, and even the ones that run RTOS, for example, this one does not have an OS. And if it doesn't have an OS, without OS, Python can't run. So the only thing that runs is something that is compiled using the instruction set of this processor. So there are compilers available for these embedded boards. Most of these vendors that produce the board, they will give you an SDE and a compiler as well. What they still don't have is how do they compile the model to these devices? And that's where AITS is working in. We take any machine learning model, including the ones coming from TensorFlow, PyTorch, Keras, and so on. There are several machine learning frameworks. We take most of those, the most popular being TensorFlow. We take that and give you a binary in the form of either a library or an executable that runs on these devices. So that's as simple and as easy as giving us the model and taking the binary out, and just flash it on the device, and you have a product that is working. Now, imagine what you could do with that. If you have an idea that nobody has thought so far, and I can give you, an empty number of ideas sitting here, that what you could do with fusing or flashing a machine learning model on a tiny device and taking it to the field, or creating a product, or creating a company with that product and distribute it to, let's say, farmers, right? If you can figure out how to use sensors that measure moisture, and based on that, you could tell that this is when you would need to water your fields, right? Advise the farmer or do something with that. Farmers would know what kind of advice and what kind of guidance do they need, right? So some of these sensors, they actually can tell you how much nitrogen, what kind of elements are there in the field, and what needs to be changed, including the distance and some of the diseases that they can capture. And your imagination is the limit when it comes to what you can do with machine learning and that data. Data comes from sensors. That data can be put and made to learn and put into a machine learning model that can again give you the diagnosis and the guidance as to what is the best way to diagnose something or remedy something in the field, in the smart city, smart homes, or smart environments, and you name it, right? So that's how easy we are trying to make this, so that people can use the technology and create a product. Any questions? I know I'm using some of the jargons, and if you have something, just throw at me and I'll try to answer that before I move on. Like I said, I want to leave you guys motivated, and then I'll share some of the tools and the resources that we are making available to the students community and the research community to create their project. But until then, bear with me and let me know if you have any questions. I'll continue to move on. So we talked about what is TinyML, right? And in that, and the benefits of those, right? The domains are, tremendous. The number of domains in TinyML or machine learning itself are many, and they create verticals in industries. So from the technology standpoint, there are 6 domains, meaning the different type of models based on your input that create these technology domains, meaning vision AI. So for example, if you have a camera or pictures, anything that you deal with pictures is essentially fall into this domain called vision AI, right? Now, if you just take that example, vision AI, as to why do you think we need TinyML or something that should be processed in the edge itself? And I'll give you a technical reason. So if you look at the number of image sensors in the world today, so yeah, let's talk about this, right? This slide talks about the global market for CMOS image sensors, and it captures the data all the way from 2013 to 2020, and then it projects as to how much would that be until 2023. So if you look at 2020, this number actually compares the number to world population. So in 2020, the world population is under 8 billion, and number of image sensors that are produced this year alone is over 8 billion. And now, why is that comparison important of people versus sensors, right? The reason it is important is that it tells you that on average, each one of us is carrying 1 image sensor, and per year. And if you assume the life of a sensor up to about 3 years, for example, your cell phone, if you're somebody like me, my cell phones run anywhere from 2 to 3 years. So typically you're carrying 3 sensors, 3 image sensors on you. And the kind of bandwidth that is needed to support those sensors is about 100 exabytes per second. So what is exa? Exa is 10 to the power 18. So 100 exabytes per second is about 10 to the power 20 bytes per second. That's the kind of bandwidth we need in the world today if you want everything connected instantly. Instead, what we have is shown in the lower right graph, which is internet bandwidth, the world from 1990 to 2018. And that is about 45 gigabytes per second. And even with 5G, it has not crossed 100 gigabytes per second. So what we need is 10 to the power 20 bytes per second. What we have is 10 to the power 10 or 10 to the power 11 bytes per second. So we are of the order of 10 away. So we need, 1 followed by 10 zeros times the speed of the network that exists today. And that would take another 30 years. I'm not saying it's very difficult. There would be progress that would be made. People will figure out, put that advance slowly, but that'll take another 30 years. Now, if we don't have that bandwidth, what is the alternate? And it is very easy to see that we will have to process some of this data on the edge device itself. Like, you don't have that option of transporting everything back to the cloud. And that is the reason that edge AI or AIoT or machine learning or TinyML is picking up, because you have to have that technology. You have to have these machine learning models running on these tiny devices. And that's just for vision AI. There are several other applications, which if I had more time, I would love to go into and tell you as to why do you need some of these technical domains to support IoT or AIoT or edge devices. But you get the drift. You get the idea that it's not a luxury anymore. It's a requirement. You need to have it, otherwise you lose the data. So for NLP, similar things. You have mobile. Some of the example I gave of biometric sensing, the fingerprint sensors. You can't send that data similar to your healthcare data. Like whatever you are going through is so private that it should be kept on the device itself. So if there is an application that somebody's offering you that, hey, take my application, it is free, I'll diagnose if you have a problem in your eye or not. And if you need to find out where the data is going. When you take that picture of your eye or whatever that is they're diagnosing, you need to make sure that it doesn't go to their server, because then you lose your private information, right? So, there are several other factors that, like I said, we can go and discuss that for hours. So what are the benefits of TinyML? Low power machine learning applications. Like I said, there are several technologies that are enabled, that are embedded in these tiny devices that make it low power. For example, wake word I talked about. When you have this entire board that is running on a coin cell battery, that's about 3 or 3.3 volt. If it is running any more than 5 milliwatts, it won't last for more than a week or maybe a month, depending on how much current it draws. So what instead engineers do is they hide the larger hardware, power-hungry hardware behind this wake word detection, which is running on few milliwatts on a DSP, which is very fast. So whenever your machine detects either wake word or a visual wake word, I'll talk about the visual wake word in a moment, then it wakes up the rest of the hardware, which is, like I said, is power hungry, but it happens only probably 50 times a day. So out of 24 hours, you are only waking up your system to about 20 to 30 minutes, which is a factor of 50. And if you don't use it, then it's infinity. So my point is, there are techniques and tips and technologies that are used to keep it low power. And it's running on embedded systems with optional cloud connectivity, making edge compute affordable with privacy and low latency. So this is what TinyML is, with these 5 things coming together is what creates the TinyML. Any questions, guys? Puneet, do you want to take up some questions? It's a good segue for me to get into the next part of the talk.
So Rohit, maybe we can finish and do the Q&A in the last, or I mean, there are a few questions, but we can do it in the end. Or did you want to do the questions now?
I would prefer now.
Okay, just give me a second. I can maybe read out some of the questions. So I think the first one is, how is TinyML related to Edge AI ML?
It's the same thing.
Same thing, yep. Okay.
But for example, Edge AI, you could have a large machine sitting on the edge. For example, your desktop. Some of the desktops or servers are very power hungry, but the latest NVIDIA server is consuming as much as 250 watts. And that's not TinyML. Like I said, TinyML is the definition where it is low power ML applications. So typically, and I'll talk about that in the next slide, this one I will talk about where that distinction is. It's mostly based on the power. So the minute you go more than 100 milliwatt to 1 watt is no longer TinyML. But it is Edge AI. For example, your cell phone or a large desktop server that is sitting in your house and is not part of any other network, it could be an edge device. The car could be an edge device. And this car, for example, Tesla, is processing about 20,000 frames per second from these 6 cameras that are mounted on the car. It is definitely edge and AI combined, but by no means it's TinyML. What is TinyML is a microcontroller that is diagnosing the speed of the piston embedded inside the car's engine. And that is TinyML because it runs on less than 100 milliwatts. So just because the device is sitting on the edge and processing AI or ML models doesn't make it TinyML.
And yeah, I think that's clear. I mean, at least it's a perfect answer. So there's another question. Why is TinyML great, and what are its applications?
Yeah, so that's the whole idea of this talk, and I'll talk about the applications as we go on. And anything that you can think of is simple enough, easy enough to port onto a small device. The idea of portability and the inexpensiveness of these devices makes it great. So for example, if you can hand a $5 device to a farmer, he can afford it. But if you provide a service with $500 per month kind of a subscription that's running on servers, barely nobody can afford it, right?
Right.
So the democratization of ML is essentially happening through TinyML, and that is the greatest thing. Some of these data centers and these high-end devices, they can't bring that democratization that TinyML will bring, and that's what I'm excited about.
And because a lot of viewers are doing VLSI in this particular year, so there are a lot of questions. How is ML useful to VLSI? I don't know. This is something you want to answer, or you have.
Yeah, so I did work for EDA companies in my past. My past life includes working for Cadence and TI and ANSYS and some of these large companies, which I joined through acquisition for the most part. So how is machine learning being used in VLSI design? Unfortunately, the answer is not as good as some of the other verticals are, and the reason is the VLSI design is still a complex flow that requires human intervention at every step, depending on whether you're designing an analog, custom, or a digital chip. You have anywhere from 6 to over 20 steps that a chip goes through, and you need to make sure that the budgets, power budgets, performance budgets, and some of the other requirements or specifications that you're given, your design stays under that. Now, there are opportunities, which means there are possibilities that these products can be augmented with some of the machine learning features. But VLSI is not ready. The market itself is not ready to accept those kind of features. And I'm talking about features, not products. It's very hard to come up with a product that works solely on a machine learning concept and is replacing an existing product. So the industry has already tried that, and it's not something new. So machine learning is purely statistical, right? Let me give you an example of a company called, I think Puneet can help me here. Puneet, there was a company in the statistical static timing analysis. It started back in 2003 or 4.
Sorry. I'm very bad in this.
Okay, so I'm forgetting the name of the company, but the idea of the statistical static timing analysis was to give you probabilities instead of definitive endpoint slacks, that there are 20 million or 1 billion endpoint slacks, And out of those, 100 are failing, meaning they're negative for the late timing analysis. Now, the product replaced those definitive pessimistic answers to probabilities, meaning they said, okay, well, 99.997% of your endpoints will pass, and there are these 0.003% that have likelihood of failing. Now, that didn't fly. And the reason it did not fly because the mindset of a deterministic result, replacing that with something statistical, was not something that most of these design teams were ready to accept. Now, given that deep learning and machine learning, they are mostly statistical, meaning they give you a number of something being as accurate as that. For example, when you say, is this my face or not, on the face recognition model, it tells you in terms of a number of percentage, like 97% or 82% or 63%. And the algorithm, the application has to decide based on a decision boundary that beyond 85%, I'll take that this is the owner of this phone, and less than that, I'll say, nope, it's not, right? That boundary has to be decided by the application. Machine learning will only give you numbers. And that's not something as a product will fly to these CAD engineers and VLSI designers. That's what has been detrimental to the rise of machine learning in VLSI. Now we can still talk about features, and there are teams who are trying, have tried, have not been successful in bringing out these features that they can roll out. EDA at this point is not commercially very R&D specific industry. It used to be, but the economy has made it so that the end customer is not ready to pay for something that has not been proven. And the EDA companies, they don't want to put millions of dollars into something that they don't know will be successful or not. So it has to start from smaller experiments and become successful. And that success has not come is essentially the reason machine learning has not found the greatness that it has found in other industries, verticals, and markets.
Okay, maybe I'll just do one more question, then you can continue, and then we'll probably take. There was one question: what is the minimum CPU requirement for running TinyML, like 60 megahertz, 1 megahertz, 20 megahertz, RAM, I guess too?
Yeah, typically depends on the application, right? If you're running a wake word, then your mic in audio spectrogram will require, depending on the sampling rate, which typically is either 8 kilohertz or 16 kilohertz, will require certain processing power. In this case, a 40 megahertz with 128 kilobytes of RAM is sufficient enough to run that application. So again, depends on your sensors, depends on the problem you're solving. There's no one definitive answer. It can range anywhere from 20 megahertz, typically from 20 megahertz to over 200 megahertz.
Yeah, perfectly makes sense. Okay, maybe we can continue, and then we'll continue with the questions after your talk.
Yeah, let's do that. So some of the distinction is actually also on this slide. If you say, look at GPU servers, right? And the GPU servers will provide you over petaflops. Flops is floating point operations per second. This is the metric that is used in the industry currently as to how many floating point operations can you shell out of a hardware per second. So this metric for GPUs is typically 10 to the power 12 or peta. For CPU, which are high-end mobile and laptops, it can be 10 to the power 9, which is giga. And for tiny machine, it could be as high as millions of flops. Okay, and that comparison for RAM is scalable between GPUs and CPUs, but when it comes down to tiny devices, the order is significant. As much as up to the order of 6. In GPUs and CPUs, it's not that high. But if you compare the carbon emission, this is another metric that people have started raising concerns over, that you're training a model that takes 200 GPU years. So they are measuring that training in terms of GPU years. That the latest and the greatest GPT-3 model that showed up was about 500 GPU years. And the kind of money that was thrown into training that model was several millions. And that generates about 455 pounds of carbon emission, which is equal to, I think, several cars. I don't remember the number, but it is a very high number compared to tiny machines, which is 11.4K, about 50 times less. So this is some of the comparison of the hardware and the TinyML, why there are advantages. It's not just latency or power, it's also environment friendly. So applications, on this slide, what you see is essentially on the x-axis increasing power and cost, and on the y-axis is floating point operations per second, the same metric that industry is using. So wake-word detection, some of the IIoT and the sensor and the vision, all these applications, they can run from 10 milliwatts to 1 watt, and that's the universe of TinyML for those applications. The boundary is still vague, and it's being debated whether we should put a line around 100 milliwatt or 1 watt. But again, there's nothing definitive. I mean, if there is an application that's taking 200 milliwatts, you can still call it TinyML. Cell phone is definitely not part of TinyML movement. So let's talk about the use case. I speak for mute, and the lady on the screen is just saying thank you. So this is how you say thank you in the sign language, for listening to my boring talk. I hope I'm keeping you guys interested and not giving you good sleep. Okay, so what is that? If you are interested, you can go on to this URL, which is the sensor app that sign language app that I'll show you in a minute, on our website. So this platform is free for students. You can register without a credit card or anything. You can get access to machines and the softwares and the solutions that are hosted on this website. And this is just one of the use cases that you can customize to your own need. And what I'm going to discuss here, some of the techniques and technologies that are used in this, and I'll take you over to the platform and show you some more. If you have interest in this or any other applications that's hosted on the machine, come talk to us. Maybe we can have you talk to some of our engineers who can help you develop your own application, right? So the architecture of the iSpeak, the application is that it takes the data from accelerometer and gyroscope, which are essentially, accelerometer is a 3D data, gyroscope is also 3D. So these are 6 parameters, and depending on the performance of these sensors, it can give you anywhere from 100 to 1,000 samples per second. So 6 data points per sample. And what we have in this is the one that I showed. This device, this Arduino board, has about 114 hertz sampling rate, which means 114 times 6 for the 6 different axes of these 2 sensors, accelerometer and gyroscope. That's where the data is collected. Now you put through the neural network, which is your inference model that we give you as a library, and then you can use that to decode, let's say, top 5 word prediction, and then to construct a sentence, you can put that into the next word predictor, and that's how you construct the sentence. And you can take that and put that to a speech synthesizer, which converts your words to speech. And so this end-to-end application, if you wear on your hand, let's say if I'm mute and I'm signing to you guys, it would convert my signs in the real time as a spoken words and a complete sentence. And that opens up a really magical experience for the mute population. And so how is that happening in the model? Is the model is shown on the bottom of the slide. Essentially 714, I think it comes from 119 hertz times 6. So that's per second sampling. 119 times 6, I think somebody should confirm this calculation is 714. And that data goes into reshape, which is an operator, and then that goes into jam, which is general matrix multiplier, and then again ReLU jam, and then you go into ReLU and softmax or sigmoid, depending on how many classes are you creating. So this is the architecture of your neural network. Fairly easy, just 3 different type of operators: your ReLU, jam, and your softmax or sigmoid, and you're done. It doesn't require a scientist to design this network. I mean, we actually even give you the notebook for free to start playing and see if your application is working or not. And you can train it, and I'll show you in a minute. If you have another wake word, then we have an application where you can constantly say that word 20 to 50 times, and it'll let you download an application that runs on these boards. You can actually also experiment with that on Ubuntu servers that we host on our website. Okay. And so that's how these devices work. The real engineering behind some of these smart speakers like Google Mini or Google Home or Google Max is essentially they capture the audio, they sample that, typically at 16 kilohertz or 16,000 samples per second. And the audio that is nothing but energy, waveform or a voltage waveform is sent to another operator called audio spectrogram. So this audio spectrogram is some kind of an FFT algorithm. Most popular algorithm to create the audio spectrogram is STFT, short time Fourier transform. So it goes to STFT, and STFT is fed to the wake word detection model, which is a machine learning model that we just talked about. And then it tells you whether the word was spoken or not spoken. So it's like wake up or not wake up. And then that signal goes to the rest of the hardware, and then it does what it does for the conversation, right? So this is how things work in real time. And you've been using some of these speakers. Some of you might be using some of these speakers. It's in your cell phone too for a number of years now. So this is the entire architecture. That's how it looks in the model. So you have a mic that goes to STFT to create the audio spectrogram, and goes to reshape, convolution, ReLU, transpose, reshape, mathmal, add, and then your output. And so this is that. Let me take you guys to the platform. Are you able to see my screen? Can you guys see the platform?
Not yet, Rohit.
Okay, I think I need to reshare.
Maybe he was just sharing the app, maybe.
How about now?
Yes, you can see it now.
Okay, so this is the platform that I was talking about. I would leave the URL with you. All you have to do And this is free for all the students and the research community. And for enterprise, we actually have a license. So large companies, they actually pay on a monthly basis to use the platform. And what you're seeing currently is the dashboard, which is talking about some of these applications that we have created and some of the users have created. And this is your sign language sensor app that we talked about, right? And I'm going to take you to the wake word detection app. All you do is go to the gallery and it'll load the training notebook that you will see. It's nothing but Python. And you can take that and you say edit in Canvas. Canvas, we actually have this platform as a creative platform, meaning think of an artist, what an artist would do. So Canvas is named after that, like how you would lay out your thoughts and ideas on Canvas to create a beautiful application. So right now it's starting the server, and in a minute we will see the notebook in Python. Okay, now that's copied on my space, and it's going to open the notebook server. Give it a few seconds and starting, and we will see the notebook server starting, the Python behind it. So this is what it is, right? And I'm not going to go through the entire Python thing because we're running out of time, but I'll give you a flavor as to what that takes. So this is essentially you upload your data sets, and I'll tell you as to how do you record those data sets in a minute. But you upload them as files, and then it creates the data set. And let me show you before I move further. So in here, you have something called palette. In palette, you can use either a file, image capture, audio capture, and live video capture, depending on your need. And I'm going in the playground, and so this is the same application that we were training there. If you want to use the application, not the training, you can use that. And once you click on that, you will see different kind of audio data sets. All you have to do is to start recording. So right now it is recording my voice. And this is the data set that is required for the background. For hot word detection, you need 3 different data sets. Number 1 is your background, meaning any sentence, any spoken conversation that does not use the hot word. That is the definition of background data set. And so let's say we have recorded enough. So I'm going to stop it, and I'm going to just say, what is it? Background BG data set. And then I would record, let's say, the audio data set, which is my hot word. And I'm going to say, come up with any hypothetical hot word, which would be, let's say, go instead of hey go, hey go, hey go, hey go, hey go, hey go. So you use different speeds and accents as much as you can. 20 to 50 would be good enough, and you call it hot word data set. And then the last one is your background noise. So we'll just be silent for 5 seconds, and I will let it record the noise. And those would be our 3 data sets. So let's do that. We're done here, and then we say noise, and then we submit. What it is doing actually is taking these 3 data sets and taking it to a script which is similar to what you see here. Okay, and then it will take you to .a or the model that you can download. So currently we are training in this tab, The training, once the training is complete, it will take us to, okay, it says likely because we are on Zoom, it's not able to record, but that's how it works. That's how the demo is supposed to work. And in terms of technology, what it is doing behind is executing something similar that you see here. And this is, for example, your, I'm going to try and see if that works. I'm going to run the whole notebook here and show you some of the how the hot word is detected in real life. And some of this is interesting. I hope it comes in time to the following cell where it starts to show testing. So this is, this is where we would test, and I'll show you how it is detecting the model. And this is running on Ubuntu. I mean, so we allow several boards, including the OS Ubuntu, which is not really TinyML, but for the development, some developers find it easy to develop on a Ubuntu and then move on to the board. So that's that. So this is what it is, right? So I wanted to show you the detection part. So I'm going to play this testing file that if you see a purple line, that means it has detected a hot word. So let's see what this is.
Canvas.
By the way, I forgot to mention that the hot word that it is trained on is hey canvas. So it's looking for the keyword canvas, and then it will tell you if there is a line, then it has detected the word, otherwise it's not.
Canvas. Canvas.
So the second one was detected.
Canvas.
Third one was detected.
Another word.
That did not detect.
Water bottled.
This one did not go.
Chair.
Did not go either.
Ceiling.
This one did not go either.
Canvas.
The last one was canvas. So that's how it detects. You can actually test and see right in the platform itself. And if you need help how to use it, you can always contact us. There is a support that we provide to the students for free. We can connect you to the engineers. And so this is how, I mean, this is, more features. So it'll take much longer for me to go through everything on this platform. But essentially what it is it's meant to simplify the life for a developer if you're planning to develop an application and bring it to your board like this. And so this, you can play around once you log in and create the account, you can play around. And if you need help, like I said, come to us and I'll connect you with some of the engineers that are working on this. And I can go on, more use cases. Surgery is one of the hot topics. There is a company called Neuralink funded by Elon Musk. What they're doing is trying to come up with a microcontroller that is running some of these models in real time to detect and communicate to the human brain. So they have shown the experiments recently, sometime in August, September timeframe, that the chip in the models were working correctly on a pig. They showed it in the conference that the model was able to detect the next frame of the pig few milliseconds before it actually made the move. So robots, the entire bone structure was predicted that this is the situation it would be in a few milliseconds from now before it happened. So that's a prediction that they showed successfully. And that means it was connecting to the waves coming from the brain and running that model in real time. And that was running on microcontrollers, by the way. So the idea of that company is to make you and turn you something similar to, character Anderson or Neo, sorry, not Anderson, Neo of Matrix. meaning you would have a chip behind your neck and it would talk to your brain, and you can learn anything or communicate newer things just by downloading a program in that chip, and the chip would communicate to your brain in real time. So it's augmented learning. There are a lot of beautiful applications of that. Probably 10 years from now, you will see whole host of newer things if that technology becomes successful. We'll see. The future will tell. The time will tell. Another one is headband to detect seizures. Now, instead of putting the chip in the body, you can have a headband today that you can wrap around in your head. And people who are suffering from epilepsy, I mean, it's generally a danger for them to go out in the real world if they don't know when they would get hit by seizures. So this band actually can detect some of the brain waves and run a model that can tell you few seconds before that the seizure is about to start, from few seconds to a minute before. And that time is good enough to find a patient, to find safety, um, before falling or succumbing to the seizures. And that's the idea behind some of these machine learning use cases. So this is what current development process looks like. You set up the hardware, like you will find, oh, this is the board I want to use. And then you acquire the data. Somehow you, for example, for ASL case, you would want to acquire the data from gyroscope and accelerometer, train the model, analyze the model, develop the app, you compile, flash, and then you monitor it, right? And we help in most of these steps, we as a company. And as simple as going to this URL, tinyml.studio, and we have host of applications and so on and so forth. And these are some of the technologies that I would spare you for now. I think I'm running short on time. It's 9:48. So I'll take questions, but before I take questions, I would like to show you once again the gallery of beautiful applications that we are busy creating. So when you have time, come here and go through some of these applications, and they are all free for you to use and create or modify or customize to your taste and need. If you have a project in your mind that is not hosted here, let us know. Either we can empower you, or when we have time, we can bring that application on this platform. Either way, we want you to learn, do new stuff, and try and create a new application on TinyML. With that, I'm open to questions. Dr. Saroj or Puneet?
Yes, thanks a lot, Rohit. Yeah, I hate to interrupt it. I think we have to have a hands-on workshop at some point. This is like really exciting stuff. Yeah, we're kind of running out of time for the next speaker coming in 10 minutes. So maybe I'll go through a few questions and we can wrap up. And I think we have actually a lot of questions. So somebody asked, like, if my question doesn't get answered, what? So what we'll do is we'll probably create a download of this chat script and maybe send it to you. And then in your time, if you can reply them, we'll send it to the the participants later, because there's a lot of questions right now. So maybe I'll go through some few of them. So the first one is, if AI can run on a microcontroller, why use a big processor like Intel or GPUs and NPUs?
Good question. So AI can run on microcontrollers, and that has been difficult until now. We are making it easy. We are the only company other than Google who's pushing in that direction. When a model comes in the last 8 years, what has been shown is generally a new research. So when it shows up on the horizon, it is pretty heavy, ranging with models from few gigabytes, and over time, the hardware improves, the models go down, and some of these miniaturization technologies that we are working on, they would improve. So a few gigabytes worth of data can be reduced to megabytes in 2 years, and that megabyte comes down to few or several hundred kilobytes in next 3 to 5 years. So it's a progress that we as a society are making continuously. Eventually, 5 years from now, what you see today would be run on TinyML. We're just pushing that boundary. Not everything is possible on TinyML, but there are a lot of things that can be done on TinyML.
Yeah, actually, I had a kind of extension question to that. I mean, most of the algorithms we are running, actually, they're pretty old algorithms, right? The ML algorithms, a lot of them have been there since 70s. It's just they didn't have the processing power, right?
Right.
So on the server desktop side, when it increased, so those algorithms started, and memory is starting to increase, the bandwidth of the memory started increasing. Yesterday we had a fascinating talk from Micron, one of the Micron's senior manager. But when it comes to microcontroller, these microcontrollers have been there for a long time. So what broke through? Like, what was it? Is it that actually the apps demanded it, so it drove the innovation in that direction? Because it looks like the algorithms were there, the microcontrollers were almost there. Why didn't these tiny ML get into the microcontrollers before? What is that driving force right now?
So what has happened in the past, right? Machine learning in 90s was hot too, but then you didn't have three things: algorithms that were needed. For example, the propagation and some of the differentiation things were not there. That couple of algorithms that came up in 2005, 2006 that started this. Data wasn't there, and the kind of compute power you needed wasn't there either. So these three things never took, they actually stopped machine learning in 90s, that
Right.
it's not successful, but people were after it, and the next decade was kind of winter, and these three things came along in 2010, and I can tell you stories, but I don't have time. In 2012 was this, that epic moment where LXNet showed that the accuracy is about 15%. Now, we as human need to experiment bigger before we start to shrink that down. Now, on LXNet, even though in 2012 it was thought that we need all 5 gigabytes of model for us to get to that 15% accuracy, apparently few years down the line, NVIDIA engineers came along and showed that if you remove 95% of that model, the 5% is only what is useful. You can run on that 5% and still produce a similar accuracy. So, it's a progress that we as humans tend to make. You need something bigger before you can start to find out what is important, what is not. So even though the larger companies like NVIDIA would have you believe that you need larger GPUs, but you don't. And that's where the push is. It is actually state of the art. It's not covered in the media as much, but you will see in the next year and from there on that TinyML people will start talking about. And once they figure out the business model, the press is behind it. Press is only chasing the money. They're not chasing the technology per se. If NVIDIA figures out a business model to make money behind these smaller, tiny devices, that's
Right.
when everybody would know. It's not about technology in the media, it's about the money, where the money is going.
I mean, I'm pretty sure there are applications where you will need a GPU and all that, but you're right. I mean, I compare it to the Windows computer, right? For 20 years, the processing power is increasing, but my Windows application seems to be the same because they just write heavier code, in a large sense. So I think you're right. Okay, so maybe we'll take just one or two more. So there's one question, can TinyML be used for applications for disaster management for establishing an ad hoc network? Not sure. Maybe. So I think maybe the question is, can we apply it on a disaster management using an ad hoc network between edge devices? I think that probably is the question. It's just an application. Seems like it can be, right? There's.
Yeah, I'm not an expert on network, but it is being used on cybersecurity, if that's what it means.
Okay. And TinyML support for RISC-V microcontrollers.
Yes, we do.
Okay.
We do support 5 based boards.
Okay. And what's the other competition for TinyML? Are there other TinyMLs out there people can use? There's another question.
So TinyML is a movement. Our company is AITS, AI Technology and Systems.
I see.
Right. So TinyML is not one company. It's a movement that was sort of created by multiple people, including us, who realized early on that the lack of business model is what is putting the idea of TinyML down. So we started, conducting some of these seminars and lectures and stuff to spread awareness. And like I said, soon, because NVIDIA has acquired ARM and they would be putting on a big show behind these technologies, and you will get to hear in the media very, very soon.
Correct. So your routines and everything, they're open source now or just free to use, or neither?
Actually, both.
Actually, I wasn't sure.
Like
algorithms have been porting. Yeah.
I lost you, Dr. Sharoj. Can you say that again?
Yeah, sorry. I think I'm just having some network issues here. I was asking, can you hear me now?
Yes.
Yeah. I think it's showing network. So Rohit, can you hear me now?
Yes, I can hear you.
Okay. Yeah, so the question was, when people want to use their algorithm, they come as just libraries, or is it open source? They can take and modify it. I think one question was related to that.
Yeah, so it's open source too. We have made our compiler open source. So if you go on GitHub, this is a URL. Part of that is open source, and part of that is proprietary. If you want to modify this compiler, go ahead, use this code and do your thing. But let me warn you, this is very complex piece of code that took the entire team for about 2 years. So consider yourself warned. It's open source if you like to modify it, but you don't even have to compile, because this platform is using that and giving machines for free that are running Deep C and Python and C++ and a bunch of other things. So you don't even have to download if you don't want to modify that. But this is given to certain non-profit organizations that are using the framework for their advantage.
Okay. So thanks, Rohit, and Puneet. You can maybe have the last word.
Yeah, so I have just one question. So it's so your resource is free for students and for institutions. What about the guys like me?
For people who are as rich as you can afford to pay anything that we demand.
Oh, okay. Then I think I have to talk to you offline then.
I think the question should be, what about me who is not in academia and don't have money?
That yeah. So I missed that particular part. Just to add that disclaimer, I don't have any money.
I was just kidding.
So
Yeah, there is no restriction per se, but we hope that it's put to good use. Is all what we're asking.
yeah. So we are looking for more and more such. I think after this sessions, it looks to me we can do a lot of tutorials and the workshops around this, and definitely we will plan something so that it helps all these students, because it looks to me there are a lot of people in the college. They want to do the fourth year project, third year project, and everyone right now they are just using this. There is a board, and they are just doing something there. But I think through this application and through the TinyML, I think they can learn a lot of things also, and they can be like yeah. So the board they are using, maybe they are not even using that particular board. So they are just asking someone just to do certain things. I think using this they can do a lot of things, and I can see like you have a lot of applications and automations also. So like no need to learn Python. Without learning Python, people can do it, but it's good if they learn it and they just make changes. So sure. So I think Squirt is awesome, right? So let's see how to move forward and just make things. And yeah, so it's maybe TinyML is not known, but maybe in over the year with you, me, and Saroj sir, we can just work something and we can just make it big.
Yeah, sure. So we let me leave you guys with one thought that we are working with selected institutions. IIT Bhubaneswar is part of that, and they likely would reach out to you guys. I don't know how is that working. I'm not involved, but there is this Canvas Scholar program that we offer to students for free. It's a 4 to 6 weeks program, which is mostly self-paced and has some projects that would want you to finish before we award the certificate. So that is one program that you might consider enrolling. I think it's going to start again in January, but keep in touch. Keep looking at our LinkedIn page, the company page, and we'll give you the idea where and when and what to do.
Oh yeah, I think that's absolutely something we'd love to do. I think.
Thank you so much. Thank you, everyone.
Yeah.
Dr. Saroj, it was good time spending with the students. Let me know if I could help in any one of your endeavors.
Yeah, we definitely will. We'll keep in touch, and this was great introduction. We'll continue with this for sure. So thanks a lot again, Rohit.
Thanks, Rohit.
Thank you. Bye now.
Okay, I think we're a little over time, so let's see if Atul is here, so we can get.
Yeah, I'm there.
Hi, Atul. How are you doing?
I'm good, Saroj, and
okay.
I see a lot of people, so yeah.
Yeah, it's been a popular webinar. I think we had almost like 350 plus even yesterday. So yeah, so we'll get started. Sorry, it ran a little bit late, but we had some good question answer sessions. So Atul, what I'll do is I'll have Mridula introduce you. You can go ahead, start, and then we'll do a Q&A after that, after your talk is over. Okay.
Sure.
Okay. All right. Thank you. Yeah, go ahead.
Thank you, sir. Now let us welcome our next speaker, Mr. Atul Bhargava. He is the principal engineer at ST Microelectronics Noida. With nearly 17 years of industry experience with ST Microelectronics, specializing TFET and FPGA, he worked with different foundries, provided their PDK support to the FPGA group. As a senior design engineer, he provided standardized backend methodologies to increase productivity. As a technical leader, he was the single point of contact for all EDA vendors to IP development teams. He evaluated, benchmarked, and deployed the best-in-class tools in all domains for memory design. As a senior staff engineer, he began gathering and prioritizing the needs of all tools across groups and sites. His key areas of work include domains such as parasitic extraction, full custom simulators, reliability flows needed for electromigration, and IR draw. He is currently working on design variability and yield improvement techniques. His contribution to the industry includes involvement in various technical evaluation committees like Gandhian Young Technological Innovation Award and other conference evaluations. He has presented papers at multiple forums representing ST like DAC conference, VLSI conference, and QUAD conferences in US, Europe, and Asia at ST dedicated to university collaborations. So now I would like to request Mr. Atul Bhargava to share his knowledge with us. So please start.
Hello, can you hear me?
Yes,
Yes,
Atul,
sir,
we
yes.
can, yeah, we can. Go ahead.
Very
Thanks.
great. So thanks, Mridula, for those kind words. I think you said a lot about me. Some of it I had already forgotten over the years. So thanks a lot for reminding me as well of what I had achieved in the past. So I hope the slides are visible, and I see that there are a lot of people who have joined in, and I will give preference to Q&A. There are certain questions that I would also like to ask in order to understand if you are with me or not. So as we continue in this journey of the next, say, 1.5 hours, let's try to be, as you can say, make this discussion a little more interactive. So first of all, thanks Dr. Saroj and Puneet, two of my good friends who invited me for this session. And as you can see, the title of this presentation is Present and Future of VLSI, Our Contribution. And when I say our contribution, it's something that I will just highlight in a few slides to explain how did we actually engage on certain topics which were interesting for the industry. Again, when we talk about the present and future, it also is very important that we look a little bit on the past. So I will work on that maybe throughout the slides, maybe just the beginning, towards the beginning of the slides. A very quick view for all of us, just to understand when we are talking about VLSI industry, what are we exactly looking at? So this is the data which was published in 2018, looking at the numbers of 2017 per se. And what we saw was that for the worldwide market of around 43 trillion euros, that essentially is being served with the help of semiconductors. The size of semiconductor was nearly 375 billion euros. So it's not a small industry, but at the same time, it's not as big as some of the other industries that you can imagine. But the total electronic industry that it serves it's quite huge, and we form the basis of this industry. So it's quite a significant contribution that we bring to the table, and a lot of people actually not just get jobs and get some super cool equipments because of us. A quick view from the India perspective. So just to mention some statistics, this is something coming from the August 2020, you can say, magazine, which published these numbers. So again, just to have a view that we are currently 3,000 chips are made in India or designed in India every year. So this is the kind of numbers that we are churning out from India, just to give the Indian view. And there are nearly 30,000 engineers working on different aspects of chip design and verification in India. This includes a lot of companies. One of them is ST Microelectronics, which I'm representing currently, and I'm working for. So this is just to give you an overview of when we are talking about VLSI industry, what exactly are we dealing with. There are 100 plus semiconductor players in India, and these vary from some big giants. If you look at the top 10, I think more than 5 or 6, 7 have presence in India. I would say big R&D presence in India, and then of course there are many small companies also which are present, and there are some which keep coming in, and some which also get acquired. So M&A has been something which has been quite frequent in our industry. Here is a quick agenda. What I will be talking about, I'll be talking about some technological challenges. And again, I'm more coming from the full custom background, so I'll talk about them more. Then some design challenges from the full custom background, as I've said. I'll be focusing on 3 examples. I would not say I will be deep diving into any of them, but I will take 3 examples, which are the DRC, parasitics, and design simulations. What is changing, what is really making or posing a challenge for us, and what we have to address in a big way. It's followed by a summary and a couple of slides just to understand And I think especially for the budding engineers, this is a very relevant question. What do you need to get in the industry? And the second question is, once you have entered the industry, what should you do in order to succeed? Again, these are very gray questions, and the answers are even grayer. But I'll try to maybe talk a few points very at the top level, and then I will invite questions if you have any specific questions to see what is it that we can do together in order to really succeed in the VLSI industry. Quickly going on the technological enhancements, I'm pretty sure most of you who have been studying VLSI have seen this. You have studied Moore's law, and you know that every 18 months we have to double the number of transistors, and most of the companies were following this very you can say legally. Maybe I can even use that term till 2005 or 10. And then many companies said that we don't want to really follow it, but there are still some companies who continue to follow it, like TSMC, Samsung, and probably Intel as well. So this is something that we have been trying, and then comes this real scare of the diffraction formula, which says that if the wavelength that you're using in order to fabricate, and if the size of the aperture is less than or equal to 1/3 of the wavelength, then you can have 100% diffraction. So anything to fabricate below 1/3 of 193 nanometer, which is the current wavelength that we are using, is a challenge. And there are multiple ways in which we have been trying to work on this. Maybe I'll not spend much time over here, and maybe I'll move to the next slides, just to showcase why this challenge, and how does it really, this challenge, percolate on the fabrication aspect. So this is what we were doing in 1990, and this is the exposure dose and the focus that we are talking about. And in order to manufacture any, you can say, any shape, each circle that you see is the variability that you can allow in order to ensure that the shape is being manufactured correctly. So for you can say, for these horizontal lines, this is the space in which you can get a good fabricated shape. Okay, so if I start combining all of the shapes that were allowed, we were able to finally see that this is the green area, or this is the area where or the region where when we were in terms of focus and exposure dose, if we were within these ranges, what was being fabricated for all these shapes together was very much fabricatable, and it made a lot of sense. This was the story till 1990s, and here what I'm showing is something which is typical to 180 nanometer or 130 nanometer. As we started moving along in early 2000, these started the probability of getting correctly manufacturing these shapes started reducing significantly. And as you can see, that what happened was we had to actually eliminate certain shapes. For example, 45 nanometer, 45 degree angles were prohibited. So what happened that it took away one of the circles, and what you see is the area which is depicting that the circuit can be, or the shapes can be really manufactured well, can start expanding. And as we progress, what we see is that today in 2020, the kind of shapes that we can fabricate is very less. And in fact, when you see these two colors, I'm sure some of you who have already worked a little bit on VLSI design would be aware of the term, which is multi-patterning or dual patterning. So here what you see is dual patterns. So instead of really using one mask to manufacture all the shapes of a given layer, we are using two masks. And then of course there is triple patterning, quad patterning that can be used. So this is the current state of affairs, that we can actually manufacture very less number of shapes. Very few shapes are allowed. And even then, the kind of window that we are expecting, which can be manufactured well, has really shrunk over these years. So this is just to emphasize on the technological challenge we are having. Of course, one way to look at it is that once EUV arrives, which we have been hearing almost for more than 10 years now, these problems will go away. But at the moment, there is no EUV, and we are forced to look into limitation of shapes, very structured or very, you can say, regular patterns that can be manufactured. So this is the current state of affairs that we are looking at. And this is true for all technology nodes, you can say below 28 or 20 nanometer. So this is just to portray that what are the challenges on the fabrication side. Of course, the other challenge is how to fabricate the device. So the planar devices are becoming very difficult to, you can say, squeeze further. So there are two ways in which you can actually gain in terms of, or you can progress further in terms of technology nodes. One is the FinFET. I think I'm pretty sure that most of you would have already heard about this. So there, what you are doing is actually, instead of fabricating something on the horizontal axis, you are actually just rotating it by 90 degrees. So you see something like this, which is actually fabrication, which is 90 degrees than what it used to be. So these are the fins. Of course, it poses some challenges, both in terms of fabrication and the analog nature of the designs, because you cannot really change the size of the gate length by any number. Now it has to be a multiple of each of these fins. So there are some challenges, but this is one technology. And the other one, which ST has been really pushing, and we have seen a lot of merit for this technology, is the FDSOI technology, where you are very close to the normal planar technology. But in order to gain that, you can say, benefits of the lower technology nodes, you actually use a very thin, you can say, substrate layer. And this is something, again, I will not go into much details on this aspect, but if you want more info on FDSOI, maybe we can have a dedicated session on that sometime later. Now, having looked at this, the other aspect, which this is a common slide that in fact I use quite often when I'm presenting, which is the design complexity. The challenge over here is that we believe that we are doing a great job as designers at making some of these state-of-the-art chips. But when you talk to our managers, when you talk to the customers, they always need more. So I've just done it in a little fun way. So the three parameters which are very well known as the PPA, the power, performance, area. So this is how we look at it, and everyone needs lesser power to be consumed by these chips. And the ideal scenario could be that it can start producing power instead of consuming it. And then I was thinking that in terms of performance, what is the fastest? Maybe the speed of light is fastest, but maybe there's something faster than that is Rajnikant. So I'd use that example. So all operations should be completed at the pace of Rajnikant. That's what ideally everyone wants. And in terms of density, all the human embedded capabilities should be within 1 mm square. This is something idealistic that we want. And whenever you ask the customer, are we on time? They always tell you, oh, we needed this chip yesterday, so you are anyways late. So it's not that you can achieve something which is incredible. So this is just the fun part of it. Now I'll talk about some of the challenges, as I mentioned, with examples. So DRC challenges, and this is something which is, if you look at it, it looks like very obvious, or maybe fine, because with these technology nodes, we are increasing the number of DRC rules, and you might say, okay, fine, this should be linear, and then there is just a slight offshoot, which is quite normal. But then I would like to remind you that look at the scale over here. This is not a linear scale. This is a log scale that I'm talking about. And actually, if you look at it, we have for 180 nanometer, where the number of DRCs used to be close to 800 or 900. This is when I started my career, and we started building some chips. And now this is more than 120,000 rules that have come into picture. Now the question is, why these many rules, and what has become so complex? Just a slide to explain to you, and I start from 130 nanometer and I go only till 28. I don't want to go further, because then there are many other complexities which probably it's very difficult to explain in a very short duration of time. But what we were looking at 130 nanometer was essentially multi-dimensional checks and how to manage them. The width and spacing rules were something which were most important. what happened with 90 nanometer, we started looking at the same checks, but they became more complex because even if you turn certain shapes, these become a little more complex in nature. So the description of these checks started becoming more and more complex. As we moved into 65 nanometer, which was close to 2008, what happened was it was not just a matter of fabricating as per rules. We also wanted to do you can say a simulative environment where we want to see because of the ambience, what is the impact on the other shapes. So those of you who are interested in optics, what can really make sense is, so you will have one peak because of the slit that you have made, or because of the slit that is available on the mask and through which the light is passing. There will be one maxima, but then there will be some more maximas which will follow, which are called as the first order or second order, third order effects. So just in order to make sure that they are not really interfering in your circuit manufacturing, we started doing some litho checks, which came into picture. And then there was certain pick checks. So as we moved on, we had some pattern matching checks, which got introduced. We saw some off-grid checks, which started becoming more and more complex, and so on and so forth. So this story is still continuing. If you look at 7 and 5, I was just reading one of the DRMs from 7 nanometer a couple of days ago, and I saw that one of the checks was written in 2 pages because the explanation of the check was so long, and it was very difficult for designers to even remember those kind of. So in order to remember those checks, it becomes very difficult for the designers, and so EDA came up with a solution which makes a little more sense. So earlier, what we used to do, and this is still, you can see the early 2000s, that we used to have a design tool, and if you are using Virtuoso or the Mentor Workbench or any of those tools, you might be knowing that we have this tool, and then it has an OA database on which we work. There is an OA real-time database, and then an OA database which is preserved in your library. Then you have to do a GDS out or an OSS out, or you can have different formats, but then your DRC engine was really sitting on top of that. What started happening in the year 2000 and 2005, around 2005, is that instead of running your checks on GDS, which was an additional step after running your OA database, we started really, you can use, or you can run your DRC engine on top of this OA database. So this is something that was introduced something in 2005, close to 2005, and it's still there, it's available. But still, this was after you have made the layout, you have to actually trigger a DRC check, and you have to check something like that. What was important is how can we enable, or how can we help the designers while they are drawing, and they don't have to really memorize these checks, which are 2 pages or 1 page long. And then what came into picture was something interesting, which was that the client can actually sit on top of your design tool itself, and you can do on-the-fly DRC. So you can actually check the DRCs while making your polygons, or while making your layers, while drawing your layers. So this is something which is almost state of the art, but it is not something that has started or introduced a couple of years ago. So this came into existence something close to 2010. I just wanted to highlight that this is something which is challenging, and which eats up a lot of time when we talk about layout validation or layout verification, so to say. We did a lot of work around these things, and this is our contribution. You can say ST's contribution. So we are primarily using the Mentor tools, and what I'm trying to showcase over here are different technologies, or where we worked, and we collaborated with Mentor in order to come up with solutions which made a lot of sense to us. So as you can see, we started working on it something close to 2007, 2008, and I have just enumerated some papers that we had published. Most of these papers are available online. If you want to go through them, you are most welcome. If you need some assistance in understanding something, please feel free to get in touch with me. Then the second challenge, which could be very interesting, and here we can be a little more interactive, is parasitic extraction. So A quick question, and maybe you can answer it in the chat box. I can have a quick look at what are you trying to answer. The question is, how do you calculate capacitance between two nets? What is the formula that you can use? So maybe I'll pause for another, say, 5 or 10 seconds. If you can key in your answers. I guess it's not a very difficult question, and everyone can still hear me. So the question, okay, the question is, how can you calculate the capacitance between two nets? And I'm talking about the nets in VLSI. So I'm talking about if there is metal one, so say there are two nets running in parallel like this. This is net A and this is net B. If I want to calculate the capacitance between these two nets, what should be the formula? So I see some answers which are coming in, and most of them have mentioned this as the answer. So epsilon A by D is something that most of you have answered. So do you think that this is the right answer? Does anyone remember that when, and this is class 11th physics, I would say, we all studied this. There are many assumptions which are used when we derive this formula. And the first assumption and the basic assumption was we are talking about parallel plate capacitance, which means that these have to be parallel plates and they have to be plates. That means the width of each of this has to be negligible. It has to be much less or close to zero when we compare it with the distance between these two plates, which is actually not true. So I see some good answers coming as well. So I see Parishita has just mentioned it's epsilon A by D plus fringe. So yes, this is precisely what I'm trying to say over here, that the formula to calculate capacitance is not so simple. Actually, when you talk about capacitance, you are talking about something more than just what we think normally. So it's actually the amount of charge that can be stored or that can be preserved between these plates, or the induced, or if I go into the electric fields, the amount of electric fields that are flowing from one plate to the other. This is what is important. So if you look at and if you do a parasitic extraction with any of the tools that are available in the market, you will see that epsilon A by D is almost close to half, or sometimes a little more over half of what is the real capacitance. So yes, I see more answers coming in. So thanks, Atati, you have added some more points over here. So actually, if you want to really calculate the capacitance between two nets, you have to look at the Gauss theorem, if any one of you remembers that. So you have to look at the total surface that is there, because there will be electric lines of fields which will be flowing, if you can see my hand, from this part to this part. These are the two. And then, of course, since this is not zero, so there will be a lot which will be flowing from the top and from the bottom, and so on and so forth. So of course, yes, what you have mentioned is correct. It's called as the fringe cap, which we are talking about, but the value of this fringe cap is not negligible. So it's quite high, and this is something which has to be taken into consideration. So what appears to be very simple calculation by for you, so we can no longer really hand calculate, knowing what is the distance between these two plates and what is the thickness and so on and so forth. We cannot actually really calculate the capacitance. So the tools have to be more than what it actually looks like. Then a few more questions, more from the design perspective. So any of you who has done an analog design, maybe you can answer this. Is a capacitance as small as few attofarads important for us? And I'm talking about, say, a 28 or a 20 nanometer node. Do you believe, and maybe you can just answer as a yes or a no, is a capacitance as small as few attofarads, say a few hundreds of attofarads, important for us? What is the frequency? Good question. Good question. So let's say it's a bit cell. It's I'm talking about a memory, and we are talking about bit cell. And if there is a capacitance which is a few hundreds of attofarads, which is being thrown in by the by the bit lines, if you are aware of that term, does it really worry if the capacitance is off by, say, a few attofarads or a few tens of attofarads? So I see a mixed answer. Most of you are saying yes, but then there are some who are saying no as well. So the answer is it depends, of course, but then yes, the answer is more or less yes. That yes, these tens or hundreds of attofarads of capacitance can actually make a difference to the final circuit. And I'll show you something in the next slide, which will make a little more sense to you. So again, another question for analog circuits, what matters, matching of capacitance or the value of capacitance? Is it the individual value which is more important, or do you think that it is the matching of capacitance which is more important? Matching. Yeah. So in case of analog circuits, yes, it's matching which can make a lot more difference. But then we should also remember that the capacitance, and if there is an active device to which a capacitance is attached, it also depends what is the resistance between the two. I mean, the resistance between this active device and this capacitor. So if the value of this resistance is very small, then even a small capacitance can actually make an impact on your active device, but not the other way around. So so this is something which, again, it doesn't have a black and white answer. I like the answer which you guys have written down, so it's quite interesting. But this is something that could be very, very intriguing, and you should start thinking of it if you're not thinking now. There are some more questions, a little more obvious, so I'll just keep a I'm just trying to eye the watch as well. So some more questions, you can think about them, you can brainstorm about them. I'll just move to the next slide. For now, I'll show you some snapshot of what a typical extraction engine actually does when we are trying to calculate these capacitances. And these capacitances are the BLT values that I was mentioning. So these are bitline capacitances. And what I'm showing with the blue line, so what I did actually is I created an array of these bit cells. So, you know, there is a memory cell which is called as a bit cell, and you can arrange these memory cells in an array so that they are accessible. And then you have a periphery circuit which is used in order to actually access or understand what's written on each of these bit cells. So the way it works is it's a huge array. It can be any size, but what I did over here is I took an array of 20 by 20. So not really 20 by 20. I took it 32 by 20. So it had 640 bit cells. And I removed, or you can say I built a dummy structure as well, just to ensure that it had the same, you can say all the bit cell was seeing the same periphery, or they were having the same environment in which they belonged. And then I was trying to extract the capacitance of these bit lines, or the internal nodes, not even the bit lines, but the internal nodes of these bit cells. And when I tried to do that with a pure 2.5D extractor, which is star RC in this case that I have mentioned, this is what I saw. So actually these bit cells are exactly the same in shape. So they should see exactly the same value of the capacitance. But what I see for each of these, and these are the samples, so from 0 to 400, these are the number of samples that I have extracted. What you see is that there is a variation which is seen. So there is a lot of deviation compared to a typical value which we see. Whereas we know for sure that these capacitance should be exactly the same. This is when we try to do it with a 2D extractor. The moment we move to a more realistic, fast 3D kind of extraction, again, I will not go into detail on what is a fast 3D extraction, but it's maybe I'll touch upon it in the next slide. It's more accurate, let's say. So when we try to work with that, what you see is that these capacitances actually started to converge. So we see a less variation, and this variation sometimes can be actually explained that there will be some local, you can say, changes on silicon, which can attribute to these. Again, whether these are golden or not, it's very difficult. But as you can see, the value of this capacitance is around 290 attofarads, and there is no practical way available to us by which we can actually measure what is the value of the capacitance on silicon. So that cannot be done. You can't build a circuit to measure this kind of capacitance, or you can't even have external probes to measure this kind of capacitance, because the error margin will be more than the value of the capacitance in this case. But this is what we saw, and then we realized that we should start moving to a fast 3D extractor. So what is, in a sense, I wanted to tell you is that even for sure the C is equal to epsilon A by D is not a good way to work. What we used to do with our traditional extractors, which were called as the 2.5D extractors, was we used to run the extraction with something more precise and create huge lookup tables, which used to define that, okay, for this width and for this spacing, what should be the value of the capacitance? And depending on that, these lookup tables were built. And when we ran the extraction, it looked at these and the values were calculated. Instead of that, when you look at the 3D, they actually solve the Maxwell's equations. So again, no point in me trying to explain you what the Maxwell equations is. I'm sure your professors can teach much better than me, and maybe they can teach me as well, because I keep on forgetting Maxwell's equations. But anyways, if you try to solve the Maxwell equation, even for a small bit cell, one single bit cell, it takes almost 12 hours to extract one net. So this is not practical. So what we came up with was a fast 3D extraction mechanism. So in Maxwell equation, if you want to solve it, you can use the finite elementary method and the boundary elementary method. So you can do a combination of these two, and the Maxwell equation can be solved mathematically. The other way is that you go for a fast 3D instead of solving both of them. So there are a couple of solvers available in the market which work only on FEM, and they don't work on BEM because it takes too much time. Or you can run Monte Carlos instead of extracting one net in absolution. You actually try to find the capacitance between 2 points. You keep on adding them, and you run a Monte Carlo in order to see when the error is below a certain, or when the variation is below a certain point. You say that this is the correct value. So this is something that we are using in most of the fast 3D extractors, and we see that the values have started appearing better. Again, we are talking about the attofarad range or sub-picofarad range. If you look at anything which has to be extracted more than 0.2 attofarads, 0.2 femtofarads, sorry, it should be okay, even with the traditional ones. But if you have to look at the values which are more or less than 0.2 femtofarad, or you can say less than 200 attofarads, then you have to look at something which is more 3D or fast 3D in nature. This is just to highlight what are the challenges which we used to imagine in our class 11th, and even in even now in our engineering, as a very simple aspect of VLSI design, but it's not so simple actually. This is another one. If you remember, in my earlier slides, I was talking about multi-patterning. So what can happen is, it's easy to say that you will fabricate something in multi-pattern. So what you see over here is red is one pattern and green is the other pattern. But what happens when they are actually fabricated? You can have deviations. You can have a delta which can creep in, and there can be a mass shift either in the Y or the X direction, because of which these extraction corners can actually explode. You might have to extract many more corners just to ensure that you are covering all the scenarios instead of the traditional corners that you were extracting. So there are multiple ways which we started working on. We worked on with our vendors and with the EDA industry, and we came up with solutions which look more promising. Some of them are listed over here. So we came up with something called as a simultaneous multi-corner. So instead of extracting every corner separately, we can do a combination of these extractions in one go, and we can even come up with a single extracted net list which can actually define all these corners. So this is something which was very essential, because otherwise the runtimes just to extract and then simulate all these corners was simply exploding. So we had to figure out something which made more sense. But again, this is only, you can say the problem is only solved by say 50 or 60%. There is a lot of problem which still needs to be solved. So just evolution of the extraction methodologies. So till year 2000, when we were using the tool by the name of Arcadia, if anyone remembers, maybe not you guys, but any of the senior guys who are attending, that used to be there. That was more of 2D. Then we came to 2.5D, which is almost all the new era tools which are available in the market, the Star RCs, the XRCs, the other tools which are coming from all the vendors. Then now we are transitioning to a fast 3D mechanism where we are looking at tools like Exact, Raphael NXT, and all those kinds. Just a transition and how the industry, and this is, we have already changed 2 tools in a span of less than 20 years. So you can see that how quickly the industry is actually evolving. Some contribution from our side, from ST side, some papers that you can see are mentioned over here that we published, and we after our work in close collaboration with these ED companies. Moving on to the third challenge that I wanted to discuss, and what I think was also discussed in the previous session, just a little bit, is on the simulation side. And as you know that we can't even manufacture 2 MOSes which are identical in nature. So they vary by a little bit every now and then. So the VT, you cannot have the exact same VT which is true for 2 transistors. So these are the kind of challenges we have, and variability is something which is very, very true for VLSI design. So everything is variable, and there is something called as LVF format, which we are trying to come up with, which enables the SOC to actually cover all these corners in one go. Again, I will not go much in detail. Maybe this slide can help you understand a little bit. Again, no need to really go into the circuit. But if you look at this, these are the different corners, the process voltage and temperature corners at which we extracted, and this is CAD, of course, the circuit. And we were expecting this circuit to actually behave, and actually, you see, it should stay at the same level. But what we started seeing was that only for very few corners, and because of this local variation, some of the samples started failing. And actually, this is something which is called as the yield loss, which can happen to your circuit. So even though most of the circuits, and if you limit yourself to only the 5 or 10 traditional corners, or the, you can say, global variations, they actually go well. You might see that all of them pass, but the moment you introduce the local variation as well, you will see that some of them start failing. So there was a need, there is still a need to manage this variation in a better way. And we are using some advanced machine learning techniques just to be sure that we are able to cover all these corners in holistically and come up with better solutions. So again, some papers that we had written over the past years on simulation and the various validations that we do with the help of these simulations. In summary, I would say that the combination of advanced technology nodes and complex design pose a lot of challenges. So it's a puzzle which is not completely solved, and I am not sure whether it can be completely solved. We have solution to problems, but they are not perfect. So there is always a room to improve. And engineers such as us are very much required in the industry to come up with more innovative solutions, which can really help us make the designs better. So in VLSI, perfection is next to impossible. Again, I say next to impossible because we all know impossible also means I am possible. So that's where we are. And I'm open to some questions on the technical aspects. Dr. Saroj, if we want to touch upon some of them, and then I'll have just 2 more slides on the other aspect, which is more to cover on the software aspect. What should we do in order to be in the industry, and how can we succeed?
Yeah, Atul, go ahead. I think we have questions coming in, so I would say just you can go ahead with it and maybe cover it in
Okay.
our Q&A.
Then we can come back. Okay. Okay.
Yeah.
Perfect. Okay. So I have just put these slides at the top of my, something which came top of my mind because every time I make such presentations, these are the typical questions that I face. So I thought, why not write them down on a slide and flash them to you. So one of the questions which is very common is, what do we need to do to get into the industry? And I was just thinking on the kind of questions that we set for the question paper, and also what do we ask in interviews. So what is most important, friends, is to keep your basics clear. Please remember that even if it's a multi-billion, you can say, MOS chip, finally, it is made up of MOSes, BJTs, and resistors, and capacitors, and diodes, and all these basic circuits. And if you understand these circuits, you have the basis right. And if you have the basis right, more often than not, you will find yourself in the sweet spot. You will be able to clear the interviews, and you will be able to go ahead and demonstrate your knowledge to the people who are trying to assess you whether you should be a part of the industry or not. Just going a little deeper, if you look at even a MOS, this is just two diodes connected together. So what I'm trying to say over here is your basics have to be very, very clear. So whatever you have studied in terms of the basics, that is something that's not going to change. The other aspect is also that, as I mentioned earlier, also in the VLSI industry, almost everything changes. So whatever you study today, in fact, what you study now is not 100% true. And this is not just VLSI. If you look at physics, and this is something that I always tell my kids as well, that you study and the models of atomic theory, what you study in class 7, then they teach you in class 8. No, what we taught you in 7th was not right. Look at this. This is a better model. Then you study something in class 9th, and they tell you oh no, 8th one was a little childish. This is what we are dealing with today. So it's the same for the VLSI industry. Whatever you study, it keeps on getting upgraded, because we have not unraveled and uncovered everything that lies there. So the skill set has to be acquired. And this is the second point that I have mentioned over here. So the skill, and it can be acquired. It's not something that you have to actually, you start believing that this is too difficult and I can't do this. If you know the problem, and you can put it, or you can split it into smaller problems, more often than not, you will find yourself being able to even cover the larger picture. You should be aware of the larger picture, but then you should be able to break it into smaller problems, and you should know how to solve each of these smaller problems. This is more important. This is practically how you can actually succeed solving bigger problems. If you try to look at the bigger problem only, you don't break it into smaller steps, you will always find it very difficult and very, you can say, eluding that, okay, this is something that we can't do. But this is not always true. And it's very important, and I have put it in this sequence deliberately. Hard work, yes, it's very important. I completely agree on that, but smart work is more important. So you have to be smart in order to solve your problems. And also, what is very, very important is you have to understand the perspective of the interviewer. So you have to understand the questions well. So spend time before answering to understand what the question is. Sometimes, especially when I take interviews, what I've seen is you hear the keywords that this is what is being asked, and I know everything about it. Let me answer that. But what we essentially forget is the question is aimed to understand something that you know, but not at understanding everything that you know. So you have to be smart. You have to understand what exactly is being asked, and not just you can say vomit out everything that you know. Be a little cautious on that. So I would say these are the ingredients that you should be aware of when you're giving the written test or interviews. Most of the written tests are more tricky in nature. They are not trying to really judge how much you know, but how well can you apply your knowledge. That's more important, I would say. Now, maybe one more slide. This is my last slide anyways. What do you need to succeed in the industry? Once you are in the industry, maybe there might be some people who are very fresh to the industry and who have just joined. So a few points over there. So since our industry is evolving, it sees a lot of new things coming in. It's very important you're a part of the change. So you bring in innovation. That's something which is very, very important. So you have to look at innovative ideas in order to solve your problems. You can't keep doing something in the same fashion again and again. So if it has to be done repeatedly, start looking at automation. Start looking at ways in which you can do it in a quicker way. And simple ideas usually possess the power to change paradigms. So the idea can look very simple. Just look at the automotive industry. The biggest innovation in the automotive industry was not perhaps the engine that was made. It was the wheel. All of us know that the wheel actually changed the paradigm of the entire industry. So be aware of that usually the simple ideas, the most basic ones, are the ones which will take you the farthest. So just to keep that in mind. Application of knowledge is very important, and you should be able to communicate also what you are thinking. So those are the other points. And sharpen what you are good at. Believe in something that you are good at. You can improve on your weakness, but you can, for me personally, as I feel that you cannot make strengths from your weakness. This is very difficult to do. You might succeed in some cases, but not always. So sharpen what you are good at. If you're excellent at something, make it outstanding. Make it something which can go beyond the imagination of others. That's more important than keep trying to make your weakness into your strength. You have to work on your weakness. I'm not denying that, but then you don't have to really push yourself at making it the best thing you are at. That's all from my side, and I'm open to questions. Maybe I can take the technical ones first, and then on the softer aspects. Over to you, Dr. Saroj.
Yes. Yeah. Thanks a lot, Atul, for we always enjoy your talk. I'm sure the participants are, and those who are aspiring for VLSI jobs, I hope they were taking notes, because there's a big chance Atul will be interviewing you at some point of time. And so I hope you made notes, especially the parasitic extraction ones. I think we're going to get a lot of emails about sending them videos now. No, great talk. Yeah, so Atul, I can kind of start with some questions, and maybe you can look up the chat window as well, or
sure,
whatever you prefer, or I can just keep asking you.
Maybe you can begin, and then I'm just opening the chat window to see if I
right.
can.
So some of the initial ones which are kind of on the top, maybe those are the ones I wrote down. I can ask. So there was one question about what are lithochecks.
What are lithochecks? Okay. So first of all, I'll have to probably go back to litho. What is litho? So lithography is the mechanism by which you actually fabricate your chips. So how you do it. I don't want to go into the history of it, lithos and graphics. So maybe you can read it on the internet. What are lithochecks is important. So usually all the checks that you do are you can say measurement based. You say that okay, this is the size, or this is the width of the minimum width of the device, or the layer that I can fabricate, and then you can have even the maximas. So these are the usual checks. All these fall into the litho checks. I would say all the measurement checks that you are talking about, they are litho checks, because they are going to ensure that the lithography is performed in the right way. So globally, it's not a new term. Maybe a less used term, I would say. Do I answer that question? I hope.
Yeah, I think so. Yeah. I hope so. From the person who was asking, that was clear. I think, I guess we were not worried about it for the longer wavelength, because it was just not in the picture before. And now with really short channels and feature sizes, that's an issue right now. Yeah. Then there's another question: challenges in the fabrication of FinFETs.
So just imagine that you were how does the doping work? So you actually bombard your silicon with impurities. This is how you do it now, and everything was going from bottom up, and this is anyways what happens in FinFET as well. But when you talk about fins, you're actually not fabricating like this, you are fabricating like this. So you can imagine that's one part of the problem. Again, I would not say fabricating FinFET is such a big problem as fabricating the lower nodes is a problem, because if you look at the first slide that I used, was the dimension that you have to fabricate. The lower you make it, and still we are using the same 193 angstrom or 1930 angstrom or 193 nanometer wavelength, then it's a challenge, because what you are trying to fabricate is very small. You see, it's less than 1/3, and even with all the lenses that you put after the light beam and just above the silicon, it's impossible to go something like 5 nanometers. So you have to use multiple masks and something like that. So there are some challenges which are additional to FinFET. Even the number of masks that has to be used in order to fabricate goes a notch up. But I think what is a bigger challenge is the lower nodes, which is even the metal 1s and 2s are becoming more challenging.
Okay, great. And one related question is parasitic effects of 3D devices compared to planar devices. I guess what they're asking is, in the planar devices, the way the parasitics were calculated, is it more challenging or is it the same?
In terms of, okay, so first of all, for device parasitics, there is something which maybe I didn't cover in the slides. Is there are certain parasitics which are very difficult to measure. when I say very difficult to measure, I mean they are not really modeled in your parasitic engine. They are a part of your device models. And this is true for planar as well as FinFETs or 3D devices or whatever you say. They're a part of that, of the device models. And then there is the other section, which is the parasitic models, where you actually put in these. So if you look at the challenges which are add-on for the devices, yes, there are few, but they are once we extract them, and there are specific tools to do that. Once we extract that, we usually put them inside our models, inside our device models, instead of putting them inside the parasitic models, because you don't want to extract them again, especially for 3D devices, since these are fixed structures. So you can have a fin, you can you can have a MOSFET with 5 fins, 7 fins, 9 fins, or something like that. So once you have extracted the real value of these parasitics, you put it inside the models, and depending on the parameters that you are passing on for that device, they are picked up from the device models, not really on the parasitic side. Again, traditionally, if you look at 180 nanometers, even the contact to gate capacitance and these capacitance were part of the device capacitance. But now, slowly and gradually, they are becoming the part of the parasitic caps. But for these layers, mostly the challenge is almost similar when you look at the planar as well as the FinFET technologies. Not much of a difference. Of course, for FinFET, since it's on the lower technology nodes, these capacitors and these resistance are much smaller. But at the same time, they make a bigger impact, because as I mentioned earlier, it also depends on the value of the resistance which is connected between these active devices and your capacitor. So if the resistance is too small, then even a smaller capacitance can make a lot of difference to you, because it's that's one of the points. The second point is that there is what is essentially going to manage the delay of your circuit. It is the RC of your device plus the RC of your parasitics. So the difference between, or the order difference between the R of RC of your device and the RC of your parasitic will really make a difference whether the parasitics are equally important or not. For example, I'll give you a simple example. For 180 nanometer, we were doing a simple CC extraction. We were not even imagining R, because the input impedance of our devices was very high. So the R of the device was so high, and the R which was being realized by the parasitics was comparatively at least 2 orders lesser. So it was not a problem. But as we moved into 90 and 65 nanometer node, instead of CC extraction, we started doing an RCC extraction, because these R became significant and they were very close to the resistance of the device itself. So that's the complexity and how we decide these stuff. Okay.
Okay, that sounds. Now, obviously ST is like in the forefront of FDSOI. Do you see a future, like, is there a winning game here, or both go side by side like FinFET and FDSI, or you think after the whole Moore hitting the wall, one of them will take off than the other one? Do you have some?
So I can't give an official answer for this. But at some point of time, they merge into one.
Okay.
If you look at the way they are progressing, at one point of time, they will merge into one. This is very clear if you look at them technically. But for the time being, I think both of them will stay. And at least for nodes like 16 or 12 till 12 nanometer, I see the need of both of them, because there are some very, very staggering benefits that you get in FDSY over FinFET. So both of them will stay. But gradually, yes, the answer is yes, they will merge into one. Which one? I don't want to say.
So right now, if you look at the market share in the sense like maybe number of wafers or the area wafer wise, I think it's mostly FDSI, or it's like half or?
I would say below 7 nanometer, it's all FinFET. We don't have an FDSY node below 7 nanometer. If you look at the nodes which are really in production today, because 7 and 5 is like 1 or 2 chips, that's it. If you look at 28, if you look at 20, then again it's both of them, and depending on the application. So if you are looking for low power, you are looking at challenges in terms of thermal heating, FDSY excels, and you will see a lot of chips in FDSY. But if you are looking at brute power, you are looking at, the computational power, then FinFET is something which gives you the benefit there. So you will see both. Again, I would not like to comment on the share per se, but both coexist for these nodes for sure. But if you look at 7 below 7 today, the kind of requirements we have, it's largely FinFET.
Now, is that because there is a physics or a process limitations right now, or what's the reason behind it? Or is that also proprietary? I mean, if it's proprietary, obviously you don't have plans.
No, I would say many years ago, ST decided not to come up with new technology nodes. In fact, we recently decided to announce the technology node with 18 nanometer. And for 18, we are FDSY based, so we will continue with 18. And this is a collaboration between ST and Samsung. It's not proprietary. It's well declared in the media as well. But below that, we are not aiming, because if you look at our market segment, we are not looking at making microprocessors.
Right, correct.
So that's the reason why we have not come up with a 7 FDSY today. Again, I'm not saying whether it is possible or not. That's a good question. But today we are looking at 28 and 18. And frankly speaking, if you look at how the industry is working, the major money, if you look, where is it coming from, is still coming from 40 and 28. It's not coming from the 7 and 5, because there are very less number of chips and the profit margins are still not that big to make it very, you can say, lucrative. We are still getting most of the money from 28, 40. And if you look at ST's money, it's even coming from 180 nanometer and even from 350 nanometers, because there are certain chips where you don't need to squeeze down the space. You need to just get a very robust design which works 100% of the time, something on automotive and stuff like that. And what sells is largely 180, 90, 65 is something which is selling like hotcakes right now. 7 and 5 is something that will come in the future.
Yeah, I think, being an analog designer myself, your talks always make me feel old because you say, we started 20 years ago in 180, but that's all we use most of the time, 180, 130. Yeah. I haven't gone beyond 130 yet. All our market share is still 130, 180. Yeah.
In fact, I think 4 years ago, I was talking about at one of the forums that we are going to make a chip in 16 nanometer for automotive. And there were a couple of car drivers who also knew semiconductor who said, oh, we are not buying that car. You might crash the car in 5 minutes. So but that's it.
Okay, cool. So there's a question on how 3D extraction can be feasible in real layout designs with computing of table lookups, and can it speed up the system of solving time?
Yeah. So lookup tables actually are 2.5D. We don't consider it as 3D. 3D means that you are actually solving the entire Maxwell's equation. So there is no way you can use lookup tables for 3D. But what you can do is, when you are making the lookup tables, you can actually run the 3D and generate those lookup tables.
Lookup tables, right?
Yeah, but then the lookup tables are as good as the test structures. The more test structures you cover, the better would be the lookup table. But then if you look at our analog designers, and we have some of them with you, you will see that the structures that they make cannot be covered. It's impossible.
Right.
It makes crazy structures because sometimes, especially if you look at the memory designers, they want to squeeze in area from anywhere. So even 0.1 micron is a huge saving for them. So you cannot come up with ideal shapes. So hence, whatever is lookup table based will have an error factor, and you have to deal with it. There's no way. Now, how can we make a 3D solver practically possible? Maybe that's something that we have been thinking since ages now. It doesn't look like if we combine both FEM and BEM, it's practically possible. Even with all the computational power we have, we can put a supercomputer with, say, 1,000 threads and then try to extract it. Still, it will take a lot of time. I don't think so that's going to become very effective very soon, because beyond a certain point, you can't even do multi-threading. You have to stick with a single thread, or maybe within 4 or 5 threads. You can't reap those benefits because you're talking about a single net. I said one net took us around 12 hours to run the complete 3D extraction. So you can't do anything about that. So I don't see it happening tomorrow. If you have an innovative idea, welcome to the industry. This is what we are looking at. We are trying to solve this problem. We have not been able to solve in the last 10 years. And we are actually looking at some very good algorithms on fast 3D today. Some very good things have happened, and we have been able to progress on the situation. But if you look at sub-auto, which we are not looking today, but if you look at sub-auto, we don't have a solution. We actually don't know how to extract anything which is less than 1 attofarads. It is not accurate.
Yeah, actually, there was a great talk yesterday by Dr. Vishal Sapani from Micron, and he had this really nice 3D picture of a vertical structure, and because he's saying that everything is kind of moving vertically, why it's sort of becoming difficult. So I was giving an example. It's like building a Burj Khalifa all the way to the moon. I mean, that's how it looks, and that got me thinking. It's like what you're doing now, right? It's like all your parasitics are actually happening in the horizontal fashion. It's not happening between plates now. Do you see like the CAD tools, like, you kind of already touched upon it, hitting a brick wall, like where you say, okay, we just can't do 2.5 anymore because the errors are just too large, because these are really, three-dimensional structures. We just can't do it. I mean, you kind of touched upon it, but like, for example, in 4 nanometer now, or 3 nanometer right now, are they able to get 2.5 with pretty good accuracy, or is that something you're already seeing?
No. So my personal recommendation is, if you are doing a full custom, especially analog, and you are anywhere below 28 nanometer, including 28, you should not be doing a 2.5D. You should not be looking at lookup tables. You should be using a fast 3D. That will make much more sense. Of course, if you are still sitting at 180 nanometer, 130 nanometer, it's fine to to deal with 2.5D. But for sure, anything below 28, please stop using 2.5D extractors. They are too dangerous. They can actually screw up. You can make a wonderful design, but if the parasitics are not in order, you know better than me. It can really make things really go off the target. So
yeah, absolutely. In analog design, for example, even in like the 2D, we have seen people just use a RC or a pi model instead of a, some other model, and then the circuit is completely off, right?
Yeah.
So here it's definitely. But I guess my question would have been: are you going to hit a wall with fast 3D now, with this structures becoming very narrow and vertical?
Yeah. So I would say fast 3D is a very liquid term. Why? Because we are saying 3D, which is ideal, which is the golden. Okay, and we are saying we are trying to make it fast. So it's all the space between 2.5D to 3D. So if I look at the solution which is present today, yes, we will hit a wall. But while we are speaking, there are many people who are also trying to improve the fast 3D and make it closer and closer to 3D. So my own expectation is that we should not hit a wall. We should the EDA should be able to catch up as quickly as possible. Even though when I joined 17, 18 years ago, I used to keep hearing from many managers that EDA is always 3 years behind design. But if you look at it practically, they are not 3 years. Actually, they are not 3 years behind. They are quite close to you. And I still believe that they will remain close to us. But just to answer, in the current scenario, the way the solvers are working today, yes, you are right. It'll definitely hit the brick, and we'll have to find better ways.
I guess the processor also, like GPUs and all that, might help with the 3D. Maybe the 3D will get a little bit more faster, and fast 3D, they kind of maybe merge a little bit.
Right. So the Monte Carlos are increasing. We can run many more Monte Carlos in order to get the value of the capacitance, which used to be difficult. So maybe I can quote some numbers. So the fast 3D solver have become almost 10x faster in the last 3 years compared to where they were in, say, 2017. So 10x is a big number, I would say.
Yeah, that's for 3 years. That's enormous speed advantage. So you're right. I think they'll just keep improving the algorithms, more faster processors,
right?
And then you have actually that will enable to do smaller feature size computers, and that'll hopefully that will help the CAD tools as well. So there's a couple of questions regarding what happens after Moore's law. You hit 1 nanometer, 2 nanometer. Are we done, or what happens?
So there are two ways of thinking at it, and when I'm saying 2 ways of thinking at it, there are 2 ways where people are thinking right now. One is what is called as more than Moore's. So you will see a lot of differentiating technologies, and ST has been almost mastering that. So we, of course, we sell a lot of the traditional CMOS, but then there is much more than that we sell. For example, BCD is a unique technology that we have. In fact, there are very few fabs in the world which have this technology, which is a combination of BiCMOS, CMOS, and DMOS. The unique thing is that with BCD 5 or BCD 4, if I remember well, this is 350 nanometer or above. Yeah, I'm talking about. But on one chip, on the same chip, you can have a MOS which is operating at 5 volts, and another MOS which is operating at 600 volts. So this is the concept of Moore's, more than Moore. So again, I'm not saying that this is the only technology. There are many other technologies where you will see that there are ways in which you can serve the market in a better way. So what essentially are you trying to do or chase with Moore's law? Moore's law, of course, Gordon Moore said something which everyone took to their heart and they started following it. It was not actually a physics law. It's just something said, and then people love to stay with it. But the essential purpose was that how can we improve that fast? So one way of thinking is, yes, we should improve the technology node, move from 7 to a 5 to a 3 and so on. That's one way of looking at it. And the second way is, how can we provide better solutions, maybe with the same technology node. So more than more is coming from there. So with the same, say 28, if I embed, say a PCM into it, if I embed an MRAM into it, can I make it better? Can I have more solution on top of it? That's one way. The second way that we have been seeing is that earlier we used to have one chip sitting on a board and it used to work. Now we are looking at multiple chips sitting on one on top of the other. So it's not just the metal stacks piling up one on top of the other and making the Burj Khalifa till the moon. It's also the chips which are stacking up. So this is another way, because essentially what you have to do is you have to fill in that same space, the amount of computational power has to increase. So that's the other way. Of course, there is a third way, which is work on EUV, which is being done, and probably we can come up with better solution. So that's on the technology side. One is EUV, by which we will have. Then another way to look at it is what other materials can we use? Can we have something which is much more powerful than CMOS, coming with, say, gallium arsenide? I think someone asked that question in the have a whole lot.
Right.
I'm not reading through all of them, but yeah, for sure, these are technologies also which are being explored. Again, gallium arsenide or any of these technologies is not even close to the dimensions we are looking at in CMOS, but it's more on the value proposition that these technologies bring than the pure technology node that we are talking about. So
correct. I mean, silicon carbide is another one which I think you guys bought a fab now, right? STMicro bought a fab, silicon carbide. That's another dimension it is going.
Correct.
Yeah,
I mean, silicon carbide. Yeah, and to be true, it adds a lot of value. If you look at the kind of chips that are coming in, of course, we are the market leaders there currently, and we hope to be there for some time as the market leaders. But this is the value addition that is more important.
Right. I mean, yeah, you know, the voltage you mentioned, actually, we just stepped out a chip in 200 volt SOIC, which has 0.18 low voltage transistor. So it has all the way from 200 volt to 0.18. But 4 years ago, we were actually using the half micron. And so when XFAB came up with 180, we were like super excited. We were like, wow, we have 180 nanometer now where we can use 200 volt transistors. So you're right. I mean, 180 nanometer is a 2-decade-old thing, but now combined with SOI and 200 volt devices, now that's a different dimension now.
Right.
Okay. So there's a guy who's asked a question about what lithography is being used at 7 nanometer and 5 nanometer, immersion or optical. I think that's definitely your question.
Yeah, it's last again. So as I said, ST is not manufacturing anymore in those nodes. Right. But yeah, it's confidential for these fabs. And even if I know the answer, it's something that I can't really talk about much. But if you look carefully at the benefits that both of them bring, you will have the answer yourself. I think you have to just look at the benefits that both of them bring to the table. But it's very good that you are talking about these technologies, because these are both of them are very advanced technologies, and I'm pretty happy that it's being taught in colleges these days. Very nice.
So yeah, I mean, I get amazed that people are talking about 7 nanometer and all that. It's you just don't find that in most colleges being talked about. And there are questions, I think there are a couple of questions like inductive effect. Is it becoming more important for smaller technologies?
Frankly, the answer is yes, but it's a mild yes, I would say. So till now, we have not seen a very huge effect coming from inductance for circuits within the chip. Even if the chip is growing in size in terms of the number of transistors and the length of the individual wires. One of the reasons is because if you look at the inductance that comes from the board, it's an order higher than the chip. So once you put it on the board, you have to actually worry about what's happening on the board rather than the chip itself. But in holistically, if you ask me, earlier we never used to extract inductance until unless we were making an inductor on the chip for an analog purpose. But slowly we are seeing even the extractors are having that capacity that they can actually extract inductance. How much is the impact on the full chip? That's a little difficult for me to answer. I would not say it's huge, because as I mentioned, it's much more from the board than the chip itself. But at the same time, I would say it's no longer negligible as it used to be. We never used to bother about it, even at 65 or 40 nanometer nodes. But the lower we go, we see that the inductance can create a little bit of trouble, especially if you are making IPs like high-speed links and stuff like that. You have S parameters which are talking about inductance effect on the serial links that you are making. So yes, it is growing, and again, not good solutions available. Welcome to the industry and try to find one.
Yeah, maybe I can add there. The reason it has not been important is because if you go by the Maxwell's equation, it's related to lambda, the wavelength. And if you take 1 gigahertz, it's 30 centimeters. So in a chip, 30 centimeter is like huge. So you have to get to like 600 gigahertz, 300 gigahertz before the inductance starts mattering, unless you're making an inductance, like you said. But now I think we are slowly getting there, because you see a lot of 60 gigahertz, 100 gigahertz chips with attofarad caps, like you said. So that I think we're slowly getting there as well.
Yeah, and just to add, because you mentioned that especially the clock tree is becoming more and more longer. It's yeah, so 30 centimeters. Yeah, go ahead.
Right, and the thing is that even if it's a clock speed of 10 gigahertz, 60 gigahertz, the harmonics are, 120, 300, 400. So that's why
right.
These are square waves now.
Absolutely.
Right.
Absolutely.
I mean, they kind of look like sine waves at those frequencies. It's very hard to get. Okay, there's like really a lot of questions coming in right now. I think I can keep you the entire day, but so what we'll do is we'll go through a few of them, but what we'll do is we'll probably take down these questions later on, maybe compile them into a few unique questions, and if you don't mind, maybe we'll email it to you and just take your time sometime to do it.
Sure, we can do that. No problems.
Maybe let's see, take maybe carrier questions. We'll start from the bottom now. I think study professional one. You can. Yeah, I think there was a question on the top. It's like, yes, my fundamentals are great, but core companies still don't call me. So,
so I'm sure Puneet can help you a lot on that, and
right. Yeah.
Talking tomorrow. So
yeah, don't miss his talk tomorrow if you really want access to that, and he can add to it.
Yeah, maybe just on top of my mind, and sorry, Puneet, if I'm already stepping in your domain, but just to answer, I would say if the top companies are not calling you, look at your CV again. Right. Maybe it's missing some key projects. Something. Usually, what we do is we put in the projects which have been done hundreds, thousands of times earlier, and the people who are shortlisting the CVs have already seen all those projects. Try to add something, and don't bluff. Don't write something out of thin air, but try to do certain projects which make more sense and can really add value to your skill set. The moment you do that, I'm pretty sure you will get a call. So I think it's more because it's a piece of paper based on which people have to be called. And if I'm just talking about myself, if I get 100 CVs and I have to just hire 2 people, I don't want to actually call 100 people and waste their and my time. So I would prefer to call 20 people or maybe 10 people. And the 10 whom I will call are the ones who have done projects which interest me, rather than people who are just differentiated based on grades. Of course, grades are important. I'm not saying that. Sorry. Especially in presence of a professor, I can never say that. but apart from grades, please try to look at your CV, especially from the perspective of projects that you have undertaken.
No, I completely agree with you. I think Shivu made a good point yesterday. Like, if you have a bad grade doesn't mean you're a bad student, or if you have good grade doesn't mean good student. It's just that when companies come in, if they have nothing else to look at, that's the best thing they can fall back on. But if you have a bad grade, but you have the 2 best patents in the world, of course, you know, two most cited papers, then of course, you know, but if you're not there, then yes, the GPA definitely matters. So that's why I tell people, take care of the GPA first, because you know, that's your lowest denomination. Everyone is going to fall back if you don't have anything. So it's this thing. But yeah, you know, kind of adding to that question, the fundamental is a necessity. You cannot go into the industry and say, I'll design circuit, but not have the fundamentals. Why you're not getting called? You know, you just address it like you said, projects, writing better resumes, maybe communication. But the fundamental is like, it is the necessity for that job. So you cannot avoid that. So that is,
maybe I'll just compliment a little bit. So I would say that the ideal interview that we take ranges from something like 5 minutes to maybe 50 minutes, or sometimes even 1 hour 50 minutes.
Right.
And I can tell you, in the first 5 minutes, and the ones where we finish in 5 minutes are the ones who disappoint us immensely on the basics.
Right.
So we begin with that. Frankly speaking, when I'm taking an interview, I'm looking at two things. Even I'm not looking at the skill set or the knowledge part. I'm looking at two things. The first one is your attitude, whether you want to learn or not. If you are given a question to which you are not aware of in terms of the answer, do you have the attitude to find the right answer? Do you want to actually struggle and find the right answer with the interviewer? That's the first part. And the second one is your aptitude. You have to be sharp. You have to keep your brains open. That's what's going to help you. Your skill set is good, and it's there in the CV. We can always look at that. And your skill set will help over a period of time once you have spent that time in the industry. Your knowledge, again, should also be complemented a lot with your aptitude, because sometimes the problem will not come to you as written in the textbook. It might pose itself in a very, very different way. So you have to be open, as I mentioned earlier as well, that if it's a large problem, you have to first break it down into smaller pieces, and then you have to solve each of it. You can't eat the full dosa in one bite. You have to first break it, right? Especially if it's a large dosa, which is the 1 meter dosa. You have to first break it into pieces, then only you can eat it. So that's the first step that you should be very, very careful about, and you should be aware of.
Yeah, and you know, I like your. I think when we were doing this DRC training, even people who are doing DRC and LVS rule decks, you said every time you write a rule, or you're checking a rule, or you're finding a bug in the rule, always find out the reason behind it. And I think that's always missing in our engineers, is like everything they do, instead of doing it mechanically, this rule is written, let me follow it. They should always ask the question, why am I doing it? What's the reason behind it? And if they keep doing it, first of all, it kind of gives them a mentality of answering questions in generality, because they're not always going to get questions which they know. And because the questions space is much larger than what they know. But if they have that mentality, they can always lead to something. And that's what good interviewers are looking for. At least, you know, that's what I look for. So yeah, that's good. So I think we are out of time. So I'll hand over to Puneet for any closing remarks, questions, and we'll try to go through this question, and hopefully we can compress them and send it to Atul for, you know, I know you're busy, but sometime if you can answer some of them, we'll send it to our participants. So Puneet, if you want to add something or ask something.
Morning, sir. So always, like you said, Atul session is always.
Yes. Yeah, so, we always wish we had more time with your session.
Yeah, it's like the two thing is good in Atul. It's like he covers the basics and he has energy. So,
yes, and
so this combination is very rare, like energy and the basics. And I think that's the message a student should also get. If they have energy, the patience, and they know the basics, they can replace Atul maybe.
I don't think he'll ever interview that position. But yeah. Okay. Well, I think that's it. Again, thanks a lot, Atul, taking time from the from your busy schedule. like I said, we always run out of time with your questions. There's, I think, like 4 times more question, I think, what we answered. So we'll try to cover it. But thanks again. So before we leave, just a quick reminder, today at 5 p.m. we have the tutorial by Rajat Bansal from Keenhead. And he's going to show you the open source flow using Skywater PDK from RTL to GDS. So definitely tune in for that. And we'll, Puneet and me also might pitch in here and there a little bit with our experience, but look forward to it. So yeah, so definitely tune in. Okay, thanks everyone. And we'll
yeah, maybe one last comment from my side.
Sure.
First of all, thanks a lot for giving me the opportunity. That's one. And I see the audience as very, very enthusiastic. Thanks a lot, friends, for your questions, because I see that I was just going through some of them while we were just closing. The questions are really good.
If you want to answer some, please go ahead. I mean, we don't have
I think I already did some of them. I was just reading this question, is more than Moore is the integration of digital and analog technology. So I would not say so, but anyways, I see many questions. So yes, you are right, but these are very good questions. And frankly speaking, friends, if you can ask these questions amongst yourself and try to figure out an answer, of course you can ask. I'm not denying that I would not be happy to answer, but you should try to answer them yourselves as well. And most of the questions I see over here just need introspection. If you just think on them, if you dwell on them, friends, let's agree to the fact that we are all engineers, and there is a basic difference between skilled labor and unskilled labor. We are the skilled part. So we innovate, we grow solutions, we make solutions. We are the ones who find answers. So it's good to ask questions, but sometimes it's even better to ask the questions to yourself and find the answers. Sometimes you might be wrong, sometimes you might be right, but that's fine. I think the biggest advantage we have is that we have the option to fail, unlike the doctors who, if they fail, we die. So we are engineers. So please try to find some of the answers yourself. Of course, I'll be more than happy, Dr. Saroj, if you send me these questions, I'll try to answer as many as possible. But friends, once again, try to answer them yourself as well. You can find the answers in your questions yourself. It'll be very helpful for you.
No, yeah, I'll just add. I mean, this is so I mean, I always preach this. I always tell people when I give a problem to students, typically they just go to Google and type that problem straight into that Google box. I said that problem is the source for your answer. If you just try solving it, asking more and more questions, that will give you the answer. So don't go searching for answers anywhere. You have the answer, you just have to spend a little bit more time. And I 100% agree with you there, Atul. So, okay. Again, thanks a lot. We'll sign off now and see you guys at, little before 5. 5, we'll start sharp at 5, we'll join. Thanks again, Atul. We'll
Thank you.
Bye. Bye, Puneet. Did you have anything, Puneet, or sign off?
That's okay, sir. Thank you. Thank you, sir. Thank you, Atul.
Okay.
Bye.
Thank you.
Bye.